Hello, and welcome to Sleep Gravity. In physics, some structures are perfectly valid on paper, but may never have appeared in nature. The equations can describe them with remarkable clarity, defining how space-time curves, how light moves, and how matter responds to gravity. But a mathematical solution does not always come with a path by which the universe can actually create it. And even when such a path exists, the newly formed structure must still endure the light, matter, and countless small disturbances that are always present around it. A state may be permitted by the laws of physics and yet remain too fragile to survive for long in the real world. You might picture a pen balanced on its pointed tip. Such a state does not violate gravity, nor does it contain anything impossible. If its initial position is precise enough, the pen may remain upright for a short time, but even the faintest vibration passing through the table, or a current of air too subtle to feel, may be enough to make it fall. The possibility of balance remains entirely valid. What is missing is simply an environment perfect enough to preserve it. White holes entered physics in a similar way, though their nature lies deep within the geometry of spacetime. They were not first discovered as strange, luminous objects in the sky, nor did they emerge from a signal recorded by a telescope. So far, no white hole has ever been observed and confirmed. The idea appeared when physicists began studying the different forms that Einstein's equations allow spacetime to take around regions of extremely strong gravity. In the simplest description, a black hole is a region that matter and light can enter, but cannot return from once they have crossed the event horizon. A white hole has the opposite orientation in time. Matter can emerge from the region inside, but no path allows matter from the outside to enter. It is often called the time-reversed image of a black hole, not because gravity suddenly becomes a repulsive force, but because the directions of the possible paths through spacetime have been arranged differently. On paper, this symmetry appears very natural. If the equations allow a region that accepts matter without returning it, they may also seem capable of containing a region that releases matter without accepting any. A collapse can be described in one direction of time, while its reverse can be written in the other. Yet something that is easy to reverse mathematically may not be easy to produce in a universe with its own history and a clearly defined direction of time. A glass falling to the floor can shatter in countless different ways because no extraordinary preparation is required for its fragments to scatter. For the entire process to run backward, however, every shard would have to rise at precisely the right moment, rotate at exactly the right angle, and settle into its proper place, while the heat released during the impact returned to where it began. The fundamental laws may not forbid each individual motion, but the entire room would need to be arranged with almost perfect precision for all of them to happen together. A single speck of dust falling in the wrong place could prevent the sequence from fitting together. A classical white hole also appears to require this kind of exceptional past. The space-time around it must not only have the correct shape, but the matter emerging from within must also appear in an order consistent with the structure as a whole. This is one reason a white hole differs from a black hole in a way far deeper than the simple image of one object pulling things in while the other throws them out. A black hole can form when matter collapses under gravity, a process nature has many opportunities to carry out. For a white hole, no comparable classical astronomical mechanism has yet been confirmed. Even so, the greatest difficulty may begin only after a white hole has already appeared. The universe does not provide perfectly sealed rooms. Between the stars, there is still thin gas, high-energy particles, light arriving from distant sources, and radiation left over from the universe's earliest era. Most of these ingredients are so weak that they have almost no effect on an ordinary star or planet. But a white hole is not an ordinary structure. If its existence depends on an extremely precise arrangement of spacetime, even a small disturbance may become a serious problem. The paradox is that matter outside cannot enter a white hole, but that does not mean it is completely harmless. A photon or a grain of dust does not need to cross the horizon to have an effect, because it still carries energy, and energy still contributes to the curvature of space-time. As it approaches that unusual boundary, an influence that began as something extremely weak may no longer remain small in the way it was far away. A white hole may therefore be threatened by the very things that never truly enter it. This would not necessarily lead to a violent explosion. A white hole might lose its defining character in a much quieter way, as the surrounding geometry changes and the paths that once carried matter outward no longer remain intact. The first thing to break would not be the matter inside, but the structure that allowed that matter to escape. An object that opens only outward could be defeated by things approaching from outside, not by passing through the door, but by distorting the path that leads to it. This is also why the question of white holes goes beyond whether Einstein's equations allow them. The deeper issue is whether nature can create the precise conditions they require, keep them sufficiently undisturbed by their surroundings, and allow them to survive long enough for a telescope to have any chance of recognizing one. If even extremely faint light and thinly scattered matter can destabilize the structure, then white holes may not disappear because the laws forbid them, but because the real universe is never perfect enough to protect them. To understand why such an elegant possibility within the equations may be so fragile, we must first look at the origin of the white hole itself, where the same geometry can contain two very different directions of time, one carrying everything inward, and another that seems to allow things only to emerge. When Albert Einstein completed the general theory of relativity in 1915, gravity was no longer described simply as an invisible force pulling objects toward one another. Mass and energy curve space-time, while matter and light move within that curved geometry. A planet orbiting a star is not necessarily being pulled by some unseen cord. It is following the most natural path available through a region of space-time distorted by the star's mass. This new perspective opened a mathematical world far broader than anything earlier physics had contained, because simply changing the distribution of matter allowed Einstein's equations to produce very different shapes of spacetime. Less than a few months after the theory was published, the physicist Carl Schwarzschild found an exact solution describing spacetime outside a spherical object that neither rotates nor carries electric charge. He completed this work under unusual circumstances while serving in the German army during the First World War. Despite conditions that were far from ideal for scientific research, the solution that now bears his name quickly became one of the most important results in general relativity. It allowed scientists to calculate how time passes, how light travels, and how orbits change around a sufficiently concentrated mass. At great distances, the Schwarzschild solution closely resembles the gravitational behavior people were already familiar with. A massive object creates a gravitational field that keeps planets in orbit or bends the path of passing light slightly. As one moves closer to the source of gravity, relativistic effects become more pronounced. Clocks near a large mass run more slowly than clocks farther away, orbits no longer follow Newton's predictions exactly, and light must travel through geometry that becomes increasingly curved. If all the mass is compressed within a sufficiently small radius, the solution also contains a boundary that light from the inside cannot cross to reach a distant observer. This boundary would later become known as the event horizon of a black hole. During the early years, physicists did not yet know how to interpret this boundary fully. Some mathematical expressions appeared to behave strangely at the horizon, leading it to be viewed at times as a place where the theory itself might break down. Later, better coordinate systems revealed that most of this unusual behavior did not belong to spacetime itself, but arose from the coordinates physicists had chosen to describe it. In much the same way that lines of longitude meet at Earth's poles even though the planet's surface is not actually torn there, a coordinate system can fail at a location where the physical geometry continues smoothly. When the horizon was described using more suitable coordinates, the Schwarzschild solution extended far beyond the region usually associated with a single black hole. The complete mathematical map contains several regions of spacetime joined together in an unexpected structure. One represented the exterior, where an observer could remain far away and watch matter fall inward. Another had the character of a black hole, where every path leading into the future moved deeper toward the center. Beside these appeared a region with the opposite causal orientation, where paths did not move toward the center in the future, but instead seemed to emerge from a region lying in the past. This unusual region is the mathematical origin of the white hole. The name white hole can easily suggest a brilliantly glowing celestial object, or something whose color stands in opposition to that of a black hole. But color plays no role in the physical definition. The word white is used only to emphasize the opposite direction of movement. A black hole allows matter to enter but not escape, while a white hole allows matter to emerge, but provides no path by which anything from outside can enter. If a light signal originates within the white hole region, it can travel outward into the surrounding universe. But if a signal from outside is directed toward that region, the causal structure of the solution does not allow it to cross the boundary in that direction. The difference lies in how past and future are organized, not in gravity suddenly changing its sign. A white hole with the mass of the sun would not push planets away simply because it has a different name. Far enough from it, its external gravitational field could look identical to that of a black hole or any other spherical object with the same mass. A planet placed in a stable orbit could still circle it, passing light would still be bent, and clocks nearby would still run more slowly than clocks farther away. Measurements based only on the external gravitational field might not be enough to reveal whether the inner region of spacetime had the nature of a black hole or a white hole. The decisive difference appears near the horizon, where the possible paths through spacetime divide into very different directions. With a black hole, an observer can send a signal inward, but once that signal has crossed the boundary, nothing from there can return. With a white hole, a signal can appear from within and travel outward, but an observer cannot send a signal in the opposite direction to reach the source that emitted it. The two structures may share the same general exterior geometry, while the relationship between past and future inside them is entirely different. This distinction is easily hidden when a white hole is described in a few simple words as a black hole running backward. That phrase is useful as an introduction, but it cannot convey the full nature of the concept. Playing a film of matter falling into a black hole in reverse would show matter flying outward. Yet a white hole is not merely matter moving in the opposite direction. The entire structure of spacetime must be reversed as well, including the order of events, the direction of light signals, and the causal relationships between different regions. The past of a black hole becomes the future of a white hole, while the central region toward which matter travels in the first case becomes the place from which matter appears to originate in the second. Spacetime diagrams often represent this difference with diagonal lines. Light always moves along certain limiting directions, creating a kind of framework for every motion that can occur. Outside a black hole, paths still have enough freedom to point inward or away from the object. After crossing the horizon, every future direction tilts toward the center, so escape is no longer a physical option. In the white hole region, this arrangement is reversed. Future paths point outward, while entering from the exterior is not among the allowed routes. Even without a complicated diagram, the deeper meaning can still be understood. In ordinary physics, a door can remain closed in one direction and open in the other because of hinges, locks, or some material mechanism. A horizon is not a door made of matter. There is no solid surface blocking an approaching object, nor any mysterious membrane pushing particles back. The geometry of space-time itself determines that certain directions of motion cannot lead to the desired destination, much as every road heading north eventually can go no farther north once it reaches the North Pole. The limit does not come from a wall, but from the structure of space and time. The fully extended solution also contains two exterior regions, sometimes described as two universes or two distant domains within the same geometry. Between them appears a structure often associated with the Einstein-Rosen bridge, a mathematical bridge that later helped inspire the idea of a wormhole. However, the bridge in the idealized Schwarzschild solution does not provide a stable passage that matter could use to travel from one exterior region to the other. In the classical description, it closes too quickly for any object moving slower than light to cross. White holes and wormholes are often placed side by side in popular culture, but they are not two names for the same phenomenon. The richness of the Schwarzschild solution shows that Einstein's equations can contain more than a real collapsing star would ever produce. A black hole formed from a star does not necessarily come with every region found in the complete, eternally extended solution. The history of collapsing matter creates a particular spacetime structure in which the black hole region appears in the future, while the white hole region contained in the idealized solution does not have to exist in the actual astronomical process. This marks an important difference between solving the full equations under conditions of perfect symmetry and asking what sequence of events the universe truly passed through to reach its present state. A mathematical map may contain paths leading into many different regions, but nature uses only those that are consistent with a system's initial conditions and history. The eternal Schwarzschild solution assumes a complete structure that has always existed. It does not describe how a star begins to collapse or how an event horizon forms. Once that history of formation is included, the white hole region does not appear automatically. It remains valid within the extended geometry. Yet no observed classical mechanism has shown how ordinary matter could organize itself to create such a region. For this reason, white holes occupy a very unusual place in physics. They are not arbitrary ideas added to make black holes seem more mysterious. They emerge when the equations are followed all the way to their complete structure. At the same time, that mathematical origin is not enough to make a white hole an astronomical object like a star, a planet, or a black hole. A celestial object needs a history of formation, must be able to interact with its surroundings, and must survive long enough to leave some detectable trace. So far, a white hole has clearly met only the first requirement in the narrowest possible sense. The equations do not immediately rule it out. The symmetry between black holes and white holes is therefore both beautiful and incomplete. In mathematics, the two regions can face one another like opposite directions within the same structure. In the observable universe, black holes have revealed themselves through the motion of stars, disks of hot gas, gravitational waves, and even images of the dark regions surrounding a horizon. White holes have left behind no comparable evidence. The difference between the two does not lie in the elegance of the equations, but in the history required for each structure to emerge from those equations and become part of nature. To understand why a region permitted by general relativity has such difficulty entering the real world, we must look more deeply at what time reversal actually means. The laws may allow a sequence of events to run in the opposite direction, but a universe filled with countless particles, radiation, and chaotic motion cannot easily arrange its entire history so that such a reversed sequence can unfold. A pendulum swinging back and forth does not easily reveal the direction of time. If a recording of its motion is played in reverse, the weight still passes through the same familiar positions, gravity still pulls it toward the lowest point, and nothing in its path appears physically unreasonable. The difference becomes clear only when friction gradually slows the pendulum. In the normal direction of time, energy is converted into tiny thermal vibrations and dispersed into the surroundings. In reverse, all of that heat would have to return to exactly the right place at exactly the right moment, causing the pendulum to swing with increasing strength, even though no visible influence is acting on it from outside. Many fundamental laws of physics do not completely distinguish between past and future. If the velocity of every particle in a system were reversed with perfect precision, the equations could allow those particles to return to the positions they had previously occupied. Two spheres colliding and then separating would still form a valid sequence if every motion were reversed. A planet could also orbit its star in the opposite direction without changing the law of gravity. At small scales, and within carefully controlled systems, the two directions of time can appear almost equal. The difficulty emerges as the number of components increases. A familiar object is not made only of the parts we can see. It also contains countless vibrating atoms, heat flowing between different regions, and light continuously exchanging energy with the environment. To return the entire system to an earlier state, it would not be enough to reverse the motion of a few large objects. The velocity of every molecule, every photon, and every tiny vibration would also need to be arranged with almost perfect accuracy. Even the smallest deviation could cause the process to depart from its previous history. A drop of ink released into water gradually spreads without any guidance. There are countless ways for the ink molecules to disperse throughout the glass, but very few ways for them to gather back into a single small drop. Spreading happens easily because most random motions lead toward that result. The reverse process is not absolutely forbidden by the microscopic equations, but it would require every molecule to cooperate in such an exceptional arrangement that nature would not ordinarily produce it. Entropy helps describe this imbalance. A state of high entropy corresponds to a vast number of possible microscopic arrangements, while a low entropy state corresponds to a much more limited set. Water and ink mixed evenly together can arise from countless different molecular positions. A drop of ink confined to one small region requires the molecules to remain concentrated within a far narrower arrangement. Large-scale systems usually move toward states with more possible configurations, not because nature deliberately chooses disorder, but because random motion is overwhelmingly more likely to lead into that larger group of states. White holes are directly connected to this asymmetry. If the entire history of a black hole were reversed in time, the matter that once fell inward would appear to be moving outward. Rays of light that once traveled toward the horizon would become rays traveling away from it. The trajectories would remain valid solutions because they would simply be the original paths, read in reverse. Mathematically, no individual step would suddenly become incorrect. But a real white hole would not be handed a complete film that had already been recorded. The universe would need to prepare exactly the right initial state so that every particle of matter, every photon, and every gravitational disturbance appeared in an order consistent with the white hole structure. The components that entered the black hole last would have to become the first components to leave the white hole. Their direction of motion, time of emission, and energy would all need to match the reversed history required by the solution. A black hole does not require the same degree of precision to form. A star may be slightly distorted, rotate unevenly, vibrate, or contain many layers of matter moving in complicated ways. If its core becomes massive enough, and no pressure can continue resisting gravity, the collapse can still proceed. Many different initial states can lead to nearly the same result, a region enclosed by a horizon. A classical white hole lies at the opposite extreme. It is not the common outcome of many different histories, but is compatible only with a very narrow range of conditions. Matter cannot leave the interior in just any way. It must emerge in exact agreement with the predetermined causal structure. A signal arriving too early, a stream of radiation traveling at the wrong angle, or a particle that does not belong to the original sequence may be enough to prevent the state from matching the idealized solution. This fragility is often hidden when a white hole is described simply as a black hole running backward. A film played in reverse is always perfect because every frame has already been recorded. The real world does not know what the next frame will be. It has only its present state, the laws of physics, and an environment that is constantly exerting influence. For a macroscopic process to run backward, the present state must contain extraordinarily precise information about everything that is about to happen. Saying that a white hole requires special initial conditions does not mean that it directly violates the second law of thermodynamics. A more accurate statement is that the classical white hole solution is associated with a past that has been prepared with extraordinary care. The equations still permit such a past, but they provide no reason for it to arise commonly in a universe where entropy is generally increasing. The difference is like the gap between a pile of sand collapsing down a slope and every grain spontaneously returning to its original position. The downward process can unfold through many different sequences of collisions. The upward process requires every grain to receive the right force, follow the right path, and stop in the right place. No single movement is necessarily forbidden, but the complete sequence succeeds only when every detail has been prepared to fit together. A black hole formed through gravitational collapse resembles the first process. Many small differences within the original star can be absorbed, radiated away, or left outside without preventing a horizon from forming. A white hole is closer to the second because its one-way outward character depends on precise coordination between the history of the interior and the geometry surrounding the horizon. The problem becomes even more difficult when the white hole does not exist in a completely isolated universe. Even if its initial state were prepared exactly, light or matter from the surrounding environment could still approach it. Those components would not belong to the original reverse sequence, so their presence would create a new history that the idealized solution had not included. In a stable system, a small disturbance usually produces only a small change. In a state maintained by an exceptionally delicate balance, even a very weak deviation may send the entire structure along a different course. A white hole therefore encounters difficulty even before the question of its lifetime is raised. It needs more than an equation that permits it. It also requires a sufficiently unusual past to bring it into existence and an environment quiet enough not to disrupt the sequence of events. The universe may be able to write this possibility into mathematics, but natural history appears to strongly favor the opposite direction. Matter collapses, energy disperses, and black holes form from many different initial conditions. This difference leads to the next question. If black holes can emerge from real stars without every atom being arranged with perfect precision, why has no comparable astronomical process been found to create a white hole? The answer lies in the way gravity transforms a star that is gradually losing its ability to support itself into a region from which light can no longer find a path back out. A star can shine for millions or billions of years because it remains in a remarkably persistent state of balance. Gravity is always pulling matter inward, while energy produced in the core creates pressure directed outward. These two tendencies remain in constant opposition, yet for most of the star's life, they hold each other in check well enough for the sphere of hot gas to preserve its shape and continue shining in space. That balance does not last forever. The fuel in the core gradually changes, nuclear reactions no longer proceed as they once did, and each inner layer must adjust to support the increasing weight of the material above it. For many stars, the process ends relatively quietly, leaving behind a white dwarf or a neutron star. In more massive stars, however, the core may cross the limit beyond which the pressure of matter can no longer resist compression. At that point, contraction continues under the influence of gravity itself. What matters is that a black hole does not require a perfect star in order to form. The star may rotate unevenly, its layers of gas may oscillate, its magnetic fields may become twisted, and the matter on one side does not have to be distributed exactly like the matter on the other. Some of its mass may be thrown outward, while the rest continues falling inward. But if the remaining core is sufficiently massive and compact, the collapse can still create a region from which light no longer has any path back out. Nature has several ways of reaching this result. A massive star may die after exhausting the fuel in its core. Two neutron stars may collide and merge into an object too massive to remain stable. An existing black hole may gather additional gas or consume matter from a companion star. These paths are not identical, but they all share a common direction. Matter gradually loses its ability to support itself, becomes compressed more deeply within a gravitational field, and enters a state more compact than before. The collapse does not require every atom to follow a precise schedule. One layer of gas may fall faster than another. Some matter may be thrown far away, and the original disturbances may be carried off as light, neutrinos, or gravitational waves. Even when the details of the history differ, the system can still move toward the same larger outcome. A black hole allows many starting points because gravity does not demand that all matter arrive at the same moment or along one exact path. Once the horizon has formed, the space-time outside gradually becomes simpler than the star that created it. The initial vibrations settle. Some of the asymmetry is carried away by gravitational waves, and the distant gravitational field can eventually be described mainly by mass, electric charge, and rotation. The original star once contained many layers, many reactions, and a complicated history. But the black hole leaves far fewer direct traces of that entire story in the space around it. This ability to move from many different states toward a relatively stable configuration is one reason black holes do not exist only in equations. Astronomers have recognized them through stars moving around invisible masses, through hot gas in accretion disks, through ripples in spacetime released when compact objects merge, and through the dark region, where light is bent strongly around a horizon. This evidence does not reveal a perfect process. It shows that a universe filled with disturbances can still produce black holes. A white hole would require a very different history. If the entire formation of a black hole were reversed, the matter that once fell inward would have to emerge in the opposite order. Layers of gas that had been thrown far away would need to return at precisely the right moment. Light that had once radiated outward would have to converge again, and gravitational disturbances that had spread through space would have to come back in exact coordination. All of these things would not merely need to appear. They would have to meet in exactly the right way to reconstruct the entire process that had taken place before. Mathematically, such a history can be written down. Trajectories can be read backward, velocities can be reversed, and a region that once received matter can become one that only releases it. Yet nature has revealed no mechanism capable of gathering countless dispersed signals, aligning them, and returning them all to the same place with the necessary precision. The difference becomes gentler to picture when compared with flowing water. Water from many different slopes can find its way down toward lower ground. Even when every drop follows a different route, it may curve around stones, divide into smaller streams, and meet again below. No one needs to arrange every path in advance, but for the water to return to every one of its original positions on the hillside, each drop would need exactly the right direction, speed, and timing. The downward flow tolerates many deviations, while the return allows only a far narrower range of motion. A black hole resembles the water flowing downhill. Once matter has lost enough of its ability to resist gravity, many different configurations can continue collapsing. A white hole is more like returning every drop to its former place, because the matter inside cannot leave in just any way. The order of emission, the energy, the direction of motion, and the relationships among the signals must all remain consistent with the geometry of the white hole region. This also helps explain why a small amount of disorder does not cause a black hole to lose its defining nature. When gas from the surrounding environment falls inward, the black hole simply gains mass. When two black holes merge, the horizon oscillates and then gradually settles again. External influences may change the object, but they do not easily transform it into an entirely different structure. A classical white hole does not possess the same flexibility. Its state is tied more closely to the history that created it. If matter emerges more slowly, if a stream of radiation appears in the wrong place, or if the surrounding environment brings additional energy near the horizon, the original structure may no longer be preserved. A white hole must do more than appear. It must continue maintaining a very particular arrangement while the universe around it remains in motion. The distance between these two kinds of objects does not mean that general relativity favors black holes through some mysterious rule. The difference lies in the way natural processes usually unfold. Matter can release energy, fall deeper into a gravitational field, and form a more concentrated region. The opposite direction requires dispersed energy to return, while matter is released in an order consistent with the entire history that came before. One side has many paths leading toward it. The other can be reached only through a very narrow range of possibilities. Black holes are not unchanging, either. They may gain mass by absorbing matter, rotate more rapidly after a merger, and, in quantum descriptions, lose energy extremely slowly through Hawking radiation. Even so, these changes occur around a structure capable of surviving ordinary disturbances. A cloud of gas passing nearby does not make the horizon disappear. It simply changes the black hole's size and motion. For a white hole, even the question of birth is already bound to the question of survival. A structure that can form only under very narrow conditions is often difficult to preserve once the surrounding environment begins to act upon it. If the universe ever created a macroscopic white hole, that object would need not only a precisely prepared past, but also the ability to endure among light, thin gas, and gravitational fields that never completely vanish. Some models of quantum gravity propose a different path, in which a white hole is not born as the direct time reverse of a collapsing star, but appears at a very late stage in the evolution of a black hole. That possibility opens a separate direction, because it does not belong to the classical formation process being considered here. Until clearer evidence emerges, the imbalance remains. We have observed many signs that black holes are created throughout the universe, while white holes still exist, mainly within histories that the equations are able to describe. One is born when matter continues along the direction gravity has already opened before it. The other requires a rare past, a tightly organized sequence, and an environment that is difficult to find in real space. That difficulty becomes even clearer when we leave the question of formation behind and turn to the place where a white hole would have to survive, because even the emptiest-looking regions of the universe still contain light and matter moving quietly through them. Between two stars may lie a distance so vast that light needs years to cross it, while most of the volume between them contains almost nothing large enough for the human eye to recognize. There is no surface, no sound traveling through it, and no clear boundary marking where the influence of one star ends and another begins. On a familiar scale, it may seem like the most complete form of stillness nature can create. And yet, that space is never truly still. Light from distant stars continues to pass through it. Charged particles are guided by magnetic fields, thin gas moves under the influence of gravity, and radiation created, when the universe was still very young, remains present in every direction. Each component may be so sparse that a vast region of space contains only a few particles of matter within a given volume, but sparsity is not the same as absence. The universe can come extremely close to a vacuum without ever becoming a perfectly sealed room. For a planet or a star, these faint streams of matter usually have only a small effect. Earth continuously moves through the interplanetary environment, receiving sunlight, being struck by high-energy particles, and feeling the gravitational influence of many celestial bodies. Yet the planet's basic structure remains intact. A star can also lose matter, gather gas from its surroundings, or pass through regions of different density without immediately losing its essential nature. These objects do not require a perfect universe around them. They form and remain stable within an environment that is always in motion. A classical white hole faces a far more delicate requirement. Its state depends not only on how much matter it contains, but also on how past and future are arranged around the horizon. Matter may travel outward, but in the idealized structure, there is no path from the exterior into the region inside. For this defining property to remain intact, the geometry of space-time must stay sufficiently close to the original solution, even as the surrounding environment continues to bring energy toward it. A photon from a distant star may have left its source millions of years before reaching the region near a white hole. For most of its journey, the photon encounters nothing unusual. It simply travels through space, along a path determined by the larger geometry, carrying an amount of energy extremely small compared with the mass of a celestial object. A grain of dust, smaller than anything the unaided eye could see, may drift across thousands of light years without causing any significant event. Yet when such components approach a structure that is highly sensitive to conditions near its horizon, their effects cannot be judged only by their original size. General relativity does not treat energy as a visitor merely passing across the stage of spacetime. Energy helps shape the stage itself. Light has no rest mass, but it still carries momentum and still contributes to the gravitational field. Thin gas, dust, plasma, and every stream of radiation alter the curvature of the region they pass through, even though the change is usually extremely small. In most astronomical situations, the effect is weak enough to ignore. Near a fragile structure such as a white hole, the same slight deviation may take on a very different significance. The difference can be compared to two bodies of water. A raindrop falling into the ocean quickly becomes part of much larger motions and barely changes the overall shape of the sea. The same drop landing on a thin film of liquid, delicately balanced across a tiny surface, may cause the entire form to tremble. The energy of the drop has not increased. The system receiving it is simply more sensitive. A white hole does not necessarily need to face a powerful stream of matter to be threatened. The danger lies in the possibility that its structure may magnify the importance of influences that would normally be extremely weak. Even if a white hole were placed far from every star, its isolation would never be complete. The cosmic microwave background fills space like the light left behind from the era when matter and radiation began to separate. Its present temperature is very low, and each photon carries little energy, but these photons arrive from every direction and continuously pass through regions that appear empty. A white hole that survived long enough would encounter not just one isolated photon, but a faint stream of radiation continuing through time. Beyond the background radiation, there is starlight, cosmic rays, and particles expelled by high-energy events. Stellar explosions can launch matter across enormous distances. Galaxies contain hot gas, extending far beyond the visible glow, and even intergalactic space holds thinly spread matter connected to the universe's vast structural web. Wide and dark space is not a place where everything has disappeared. It is simply a place where matter has been stretched more thinly than ordinary human senses can detect. Gravity also does not stop at a fixed boundary. A distant galaxy still makes a tiny contribution to the overall geometry. Moving objects create disturbances that travel through spacetime, and major mergers can send gravitational waves far beyond the places where they were produced. When these ripples pass through Earth, the distortion is so small that extraordinarily sensitive instruments are needed to measure it. For a structure that depends deeply on the arrangement of its horizon, the idea of something being too small to matter cannot be applied too quickly. Time makes the problem deeper. An influence that is extremely weak for a single moment may leave almost no trace, but a macroscopic white hole surviving for thousands, millions, or even more years would remain continuously exposed to its surroundings. Every passing photon carries a little more energy. Every approaching particle of gas adds another disturbance, and the gravitational field around it keeps changing as other objects move. Long-term survival would require the white hole to preserve its unusual structure not only through a single event, but through the entire history of these interactions. This gently reverses a familiar intuition. A long lifetime is usually taken as evidence of durability, because an object that has survived for a long time seems to have endured many challenges. For a white hole, however, more time also gives the universe more opportunities to push its state away from the ideal configuration. A structure that exists only for an instant may disappear before the environment has time to produce a major effect, while a long-lived white hole must preserve a rare balance through countless passages of light and matter. Beneath this quiet background lies a deeper layer, where the quantum physical meaning of a vacuum differs from absolute emptiness. Quantum fields remain present even when no ordinary matter particles are detected. Their lowest energy state is not a perfectly motionless plane, but contains fluctuations tied to the quantum nature of reality. These effects become decisive only under special conditions, so they do not yet need to be treated as a direct answer to the fate of white holes. Even so, they remind us that removing every possible influence from a region of spacetime is not as simple as pumping all the air out of a box. Perfect isolation is already difficult to achieve in a laboratory, where people can build walls, lower temperatures, and create a vacuum with specialized equipment. On an astronomical scale, there is no shell protecting a white hole from incoming light, and no way to keep the surrounding gravitational field completely unchanged. Vast distances only weaken these influences. They do not erase them from the object's history. What is striking is that a white hole appears to possess a powerful protective mechanism. Nothing can enter it. If a cloud of gas approaches, the causal structure does not allow it simply to cross the horizon as it would when falling into a black hole. Intuition may view this as a perfect defense. If matter cannot reach the deeper region, it may seem that it cannot harm the white hole either. But the horizon is not a shell separated from the gravitational field outside it. It is part of the geometry of space-time, and that geometry responds to all the energy present around it. A photon does not need to cross the horizon to contribute to the curvature nearby. A stream of gas does not need to touch the interior to alter the total mass or change the way paths of light are arranged. Entry may remain forbidden to matter even as the shape of the exit has already begun to change. This fragility would not necessarily create a noisy spectacle. No cracking sound would travel through space, and there might be no flash bright enough to announce that the structure was changing. Everything could begin with a stream of energy too weak to concern an ordinary object, then gradually become important as it approached the horizon. A place that seems isolated from the entire universe may still depend profoundly on what is quietly arriving from outside. The space between the stars keeps its appearance of stillness. Light passes without sound, particles of gas drift across immense distances, and ancient radiation continues to spread a very faint thermal background through space. This quiet is enough for planets to orbit stars, for clouds of gas to survive for millions of years, and for galaxies to move past one another at an almost imperceptible pace. It may still not be quiet enough for a white hole. As streams of radiation approach the horizon, a particular effect begins to emerge. Energy that was extremely small far away may become concentrated and shifted in a way that causes its influence to grow within the description near the white hole. This is where the sparsity of the universe no longer guarantees safety, because the light is not merely passing through a region of space-time. It is approaching the boundary on which the white hole's entire existence depends. A ray of light may leave its star long before encountering anything remarkable. It crosses vast expanses, passes through thin clouds of gas, glides beyond distant galaxies, and continues carrying the pattern of oscillation it acquired where it was born. For most of that journey, the photon meets almost no resistance. There is no air to slow it. Dust is too sparse to alter its path significantly, and even the greatest distance only makes the journey last longer. If that ray of light approaches a white hole, the calmness of everything that came before begins to change. A white hole has no solid surface for light to strike. There is no brilliant shell, and no material door closing in front of the photon. Its important boundary lies in the arrangement of space and time. Light still moves along paths allowed by relativity, but near the horizon, those paths no longer have their familiar form. To understand this change, we can begin with an effect that appears in many regions of strong gravity. When light travels away from a powerful gravitational field, its wavelength may become longer. Its frequency decreases, and the energy measured by a distant observer becomes lower. This phenomenon is known as gravitational redshift. In the opposite direction, light moving deeper into a gravitational region may be measured at a higher frequency, with a shorter wavelength and greater energy. This is called blue shift. The name suggests colors, but most of the important changes extend far beyond the narrow range of light visible to the human eye. A photon may begin in the radio part of the spectrum and later be measured at a higher frequency. If the effect becomes strong enough, the radiation can move through the infrared, visible light, ultraviolet, and beyond. What changes is not merely color, but the amount of energy associated with each cycle of oscillation. Near a white hole, blue shift becomes especially significant because of the structure of the horizon. A signal from outside may approach that boundary, but there is no path allowing it to continue into the interior in the way matter crosses the horizon of a black hole. The photon still follows a valid trajectory, yet that trajectory is drawn increasingly close to the horizon, binding the signal more tightly to the region of spacetime where the white hole maintains its defining character. It can be pictured as a series of ripples moving toward a narrow shoreline. Far away, they are separated by wide spaces and barely affect one another. As they approach, the shape of the shore guides the ripples into the same confined region, shortening the distance between them, while energy once spread across a broad surface begins to concentrate. No individual ripple suddenly becomes stronger because new energy has been added from outside. The change comes from the way the entire flow is directed into a smaller area. Light near a white hole horizon experiences a similar concentration, though the true mechanism takes place not on water, but within the geometry of space-time. Signals, arriving at different times, may be compressed closer together when described near the boundary. At the same time, their frequencies rise through blue shift. A stream of radiation that was weak and sparse at a great distance takes on a different significance as it enters a region where both the intervals between photons and the energy carried by each photon are changing. If there were only one isolated ray of light, its initial influence might still remain extremely small. The difficulty is that the space around a white hole never contains only a single photon. Cosmic background radiation arrives from every direction, starlight continues to pass through, and thin gas and high-energy particles remain present even in the darkest regions. Each component carries very little energy, but a white hole that survives for long enough would be continuously exposed to streams of signals like these. Far away, they form only a faint background spread through space. Near the horizon, the geometry begins to gather that long history into a narrower region. Photons that left their sources thousands or millions of years apart may all contribute to a layer of radiation concentrated close to the boundary. The weakness of each individual signal does not disappear, but their number, their rising frequency, and the way they are compressed together make their combined influence increasingly difficult to ignore. Physicists have sometimes used the image of a blue shift curtain to describe this accumulation. It is not a visible membrane like the surface of a star, nor a shell of matter surrounding the white hole. The phrase simply suggests a region where incoming radiation is shifted to higher energies and gathered near the horizon, forming a layer of influence that grows steadily stronger within the surrounding geometry. At first, light can be treated as a signal moving through a space-time that has already been established. The geometry is held fixed, and the problem is simply to determine which path the photon will follow. This description works when the energy of the radiation is negligible compared with that of the central object. General relativity, however, does not allow energy to remain forever a passive observer. Light carries momentum, and both momentum and energy contribute to the curvature of space-time. When the radiation becomes sufficiently blue-shifted and concentrated, it begins to alter the very region that produced the blue shift. The white hole geometry drives energy toward the horizon, and that concentrated energy then pushes the geometry away from its original structure. No mysterious loop is creating energy from nothing. This is feedback between matter and spacetime. One guides the motion of the other, while the other simultaneously helps reshape the very structure that directed it. This feedback is what makes a white hole so fragile. When a black hole receives additional matter, it generally becomes more massive, and its horizon can expand to enclose the new material. Infalling matter does not destroy the black hole's basic character. A white hole, by contrast, depends on a horizon with a very particular causal orientation, where matter is allowed to emerge but no path leads inward from outside. As energy becomes concentrated near that boundary, the structure begins to adjust. No major collision is needed to start the process. A thin cloud of gas, a faint stream of photons, or a disturbance that seemed insignificant far away may be enough to create the initial deviation. The threat does not come from any obvious strength in the surrounding environment, but from the way the geometry itself allows a small influence to become increasingly important. This is also why the statement that nothing can enter a white hole can create a false sense of protection. Matter truly cannot cross the horizon within the idealized structure, but it can still approach closely enough to help alter the horizon itself. A person does not need to step into a room to bend its doorway. Weight applied in the right place may distort the opening before anyone passes through it. Of course, a horizon is not a material doorframe, and light does not exert pressure in the same way a hand pushes against a surface. The comparison rests on only one point. The boundary is not independent of its environment. It exists because of the way space-time as a whole is arranged, and that arrangement always responds to the energy present around it. As the energy near the horizon increases, the location of the boundary may begin to shift. Paths of light that once led outward may no longer connect to distant space in the same way. A new structure starts to emerge, not as a wall suddenly rising into place, but as a gradual change in the future direction of possible paths. The matter inside may not have disappeared, yet the route it was expected to use for escape is becoming increasingly difficult to preserve. What is remarkable is that the entire process may unfold very quietly. From far away, there need not be any brilliant flash marking the moment the instability begins. Light continues to approach, gas continues to drift past, and the surrounding space still appears so sparse that it is almost empty. The change lies deep within the structure of time and light, where small signals are being compressed near a boundary that was never truly separate from the universe outside. This is where the strange nature of a white hole becomes clearest. It is defined by allowing everything to move only outward, yet the things approaching it can still make that outward path unstable. No photon needs to penetrate the deeper interior. No grain of dust needs to reach the place from which matter is emerging. Their mere approach, carrying energy whose influence is amplified by the geometry, is enough to make the white hole's long-term survival far more difficult. In an idealized solution, the horizon can remain fixed while the blue shift continues to increase without limit as a signal moves ever closer to the boundary. In the real universe, space-time cannot remain unchanged in the presence of an increasingly powerful concentration of energy. Before the mathematical quantities can reach infinite values, gravitational feedback becomes important, and the original solution no longer provides a complete description of the system. The white hole cannot preserve its original form while pretending that the surrounding layer of radiation does not exist. A new structure may then envelop the white hole region, redirecting future paths and preventing matter from escaping as expected. The precise process depends on the model, the amount of matter involved, and the way the energy approaches, but the general conclusion is already becoming clear. The seemingly absolute protection of a white hole may also be its greatest weakness. In the 1970s, Douglas Eardley examined this very problem. Rather than asking whether a white hole was mathematically valid, he placed it in an environment containing real matter and studied how its horizon would respond. The result did not describe an object being torn apart by some enormous collision. It suggested a quieter fate, in which even a small amount of accretion could cover the outward passage, causing the white hole to lose the very property that had defined it from the beginning. By the early 1970s, white holes remained a strange possibility hidden within the extended solutions of general relativity. Physicists knew how to describe a region of spacetime that allowed matter only to emerge, and they understood that this structure was related symmetrically to a black hole when the direction of time was reversed. What was missing was not part of the equations, but a more practical question. If a white hole were placed in a universe containing matter and radiation, how long could it remain unchanged? Douglas Eardley approached this problem in 1974. Instead of preserving the white hole within an idealized and completely empty space, he allowed the surrounding environment to become part of the calculation. Even a small amount of matter moving toward the horizon was enough to test whether that elegant mathematical structure could truly withstand the disturbances that every celestial object must encounter. The question may sound simple, but it reaches the deepest weakness of a white hole. A black hole can receive additional matter and still remain a black hole. Infalling gas increases its mass, the horizon expands, and the system gradually settles into a new configuration. A white hole cannot adapt so easily, because its defining nature depends on a boundary that opens only outward. Matter from outside cannot cross the horizon in the idealized solution, but the energy it carries still contributes to the curvature of space-time around that boundary. Eardley realized that this small influence would not necessarily produce only a correspondingly small change. As matter approaches a white hole horizon, its gravitational effect can shift the horizon's position and shape. A new boundary with the character of a black hole horizon begins to form outside the original region, surrounding the place that was previously expected to release matter. The exit is not destroyed by a violent collision, but it may be covered before anything inside has time to escape. The phrase, "the death of a white hole," has been used for this process. Even though no object is necessarily destroyed, the mass remains, space-time continues to exist, and the external gravitational field can still influence the surrounding environment. What disappears is the causal structure that once made the object a white hole. A region that was open only toward the outside becomes enclosed by a future horizon, where the paths of escape no longer lead into the distant universe as they once did. This transformation does not require a star to plunge toward the object, or an enormous cloud to surround it completely. In Eardley's model, even a small disturbance can grow into a decisive change, especially if the white hole survives for long enough. The more time the environment has to bring matter and radiation near the horizon, the more fragile the idealized structure becomes. This can be compared to the difference between a valley and a very narrow mountaintop. A ball resting at the bottom of a valley may be nudged slightly to one side and then roll back toward its original position. The state is stable because a small deviation is not enough to carry the ball out of the low region. But if the ball is balanced exactly on a sharp peak, even the slightest shift will move it away from equilibrium, after which gravity continues pulling it farther. The original force may be weak, but the structure of the state causes the deviation to grow rather than fade. In this sense, a black hole is more like the bottom of the valley. It may vibrate after absorbing matter or following a merger, but those disturbances are usually radiated away as gravitational waves, allowing the system to settle into another stable black hole. A classical white hole resembles the state balanced on the narrow peak, where the past, the horizon, and the outward flow of matter must all be arranged in precisely the right way. Once new energy appears around the boundary, the system has no simple path back to its original configuration. The instability does not arise because the white hole lacks strength. An object may contain an enormous amount of mass and still be fragile if its defining character depends on how space-time is organized. Strong gravity does not guarantee survival. In fact, the gravity of matter outside becomes the very cause of the structural change. The paradox is that a region that seems impossible to enter can still lose its nature because of things that never cross its boundary. In an idealized description, matter from the white hole can continue escaping according to the predetermined history. Once a layer of external matter is added, however, the system's total energy changes and the geometry must be recalculated. The horizon does not remain in its original position simply because the first solution placed it there. It responds to all the matter present, including the material that is still outside. A new future horizon may expand far enough to surround the white hole region. Once this boundary forms, matter that once had a path outward now lies within a region where every future direction is trapped. The white hole does not turn into a black hole in the way a material changes color or an object flips over. The entire difference lies in the direction along which possible paths can continue through time. For a distant observer, this process may not have one clearly defined moment resembling a light suddenly switching off. An event horizon is a global structure dependent on the future of signals rather than only on the state of the system at one instant. To know whether a ray of light truly escapes, its entire later path must be known. A region that appears capable of releasing matter in the present may already lie inside the new horizon when the complete history is taken into account. This makes the fate of a white hole difficult to describe through a single dramatic scene. No crack spreads across a surface because a horizon is not a material surface. There is no sound of impact because sound cannot travel through empty space in the familiar way. The change unfolds within the geometry, as paths that once opened outward gradually cease to connect with the exterior. From far away, an observer may notice only that a compact object is beginning to behave more like a black hole. Airdley's result carried considerable weight because it narrowed the distance between a mathematical solution and an astronomical object. Before then, one could say that white holes existed within general relativity and allow the story to end with the symmetry of the equations. His work showed that the validity of a solution is not enough. A structure that is to survive within the universe must withstand unavoidable disturbances, and the classical white hole appears to fail even this basic test. The result also helps explain the silence of the sky without requiring the claim that white holes are absolutely impossible. If they formed in the early universe or through some mechanism that remains unknown, large and long-lived versions might quickly be altered by the matter around them. A newly formed white hole might not preserve its defining character long enough to produce a distinct signature. By the time its light had crossed a great distance and reached a telescope, the original structure might already have been covered by a black hole horizon. In the early universe, the problem becomes even more severe. The density of matter and radiation was far greater than it is today, so a white hole would not have existed in sparse, nearly empty space, but within an energy-rich environment. Streams of passing matter, intense radiation, and the overall expansion of spacetime would create a problem far more complex than that of an isolated state. If even a small amount of accretion is enough to destabilize a white hole, the dense environment of the early universe could hardly have offered it a quiet refuge. Even so, the 1,974 results should not be extended into a claim that every structure with white hole-like properties has been ruled out. The study focused on classical white holes under specific conditions, especially objects large enough and long-lived enough for disturbances to develop. Models of quantum gravity, extremely brief transition phases, or very small remnants may involve different conditions. None of these possibilities has been confirmed, but they leave room for physicists to examine whether the classical instability applies in the same way at every scale. The deeper value of Airdley's work lies in the way it changed the question. Instead of asking only whether the equations permit a white hole, physicists must ask how such a structure responds to a photon, a layer of gas, or the slightest deviation in its initial conditions. This new question is more realistic, because nature does not create systems that are completely isolated from the rest of the universe. An astronomical object does not live alone inside a formula. It must share spacetime with other sources of light, feel the influence of surrounding matter, and respond to every change in the gravitational field. A black hole can absorb those influences and continue to exist in a new state. A white hole, by contrast, carries an outward passage shaped by an exceptionally special history, allowing every approaching influence to redirect that history along a different path. The fate Airdley described is not a dramatic one, but its silence is precisely what makes it remarkable. A white hole may fail to release all of its matter, not because some outside force shatters it, but because the surrounding geometry quietly rearranges itself. A new horizon expands, the original region is enclosed, and the object continues to exist under a different name. At this point, the phrase, "the universe destroys a white hole," begins to take on a more precise meaning. The universe does not erase the white hole from the equations, nor does it necessarily destroy its mass. The surrounding environment needs only to bring enough energy close to the horizon for the outward passage to lose its original orientation. Once the future paths of light have been altered, the white hole has lost its most important defining property, even if the region of space-time inside still remains. The next question lies at the newly formed boundary. If the matter inside has not disappeared, but its route of escape has been covered, how does the transformation into a black hole actually unfold for light, the horizon, and a distant observer? The answer is not found in an explosion, but in the way every future direction is rewritten around the region that once served as the exit. From a great enough distance, a white hole becoming unstable may reveal no clear moment of ending. There is no surface being crushed, no shell cracking apart. Its mass remains, its gravitational field continues to bend light, and the region of spacetime inside has not been erased from the equations. The decisive change occurs somewhere more abstract. The future available to the matter within is no longer the same. To understand this transition, we must leave behind the image of a horizon as a door fixed in space. An event horizon is not made of matter, has no thickness like a wall, and does not glow so that an observer can identify its position. It is a boundary separating two groups of possible paths. On one side, light can still travel outward and eventually reach distant observers. On the other, no signal, no matter how fast it moves, can connect with the far reaches of the universe in the future. For a black hole, this boundary is oriented toward the future. Matter can travel inward from outside, but once it has crossed the horizon, all of its future paths remain confined to the deeper region. A white hole has the opposite structure. Paths may begin within the interior and open outward, while no physical trajectory from the surrounding environment can continue through the horizon in the inward direction. This opposition sounds perfectly clear when expressed in words, but the horizon can preserve this character only while the surrounding geometry maintains the necessary structure. When new energy approaches, it changes the curvature of space-time. Paths of light that once led toward distant space begin to tilt differently, and the boundary separating them shifts along with the gravitational field as a whole. In simplified models, external matter can be represented as a very thin shell falling toward the white hole. This shell has not entered the interior. It is merely drawing closer, while carrying its mass and energy with it. The gravitational field, however, does not wait until an object crosses the horizon before responding. Even while the shell remains outside, the system's total mass has already changed, meaning that the paths of light around the central region must be calculated again. A horizon with the character of a black hole may form outside the original white hole horizon. This new boundary does not need to touch the interior in the way two physical objects collide. It expands through the structure of space-time, enclosing paths that had previously been expected to escape. Once the entire history is taken into account, some of the light that once belonged to the white hole's outgoing flow can no longer reach the distant universe. The exit is not closed by a barrier. The very meaning of outward has changed. A ray of light emitted from the white hole before the disturbance appeared may still escape and continue traveling through space. Another ray leaving the interior only slightly later may encounter an altered geometry in which its future direction no longer leads far away. Two photons may originate in the same region and move at the same speed of light, yet only one belongs to the portion of history that remains connected to the universe outside. The boundary between those two fates is the new horizon. The way a horizon is defined has an unusual quality. To determine whether a location lies inside a black hole, it is not enough to examine spacetime only at that particular moment. We must know where rays of light leaving that location will travel throughout the entire future. If they eventually escape to great distances, the location lies outside the horizon. If no signal can ever reach the distant universe, it belongs to the interior. Because the horizon depends on the future, its formation is not entirely like a wall being constructed at one definite moment. In a global description, the black hole horizon may extend backward to times before the external shell of matter has approached the central region. A local observer may not yet have seen the accreting matter pass nearby, but the future history has already determined that some signals emitted at that time will never reach distant space. This does not mean that the future physically reaches backward and changes the past. No information is sent backward through time to warn the horizon that it must expand. It is simply a consequence of how the boundary is drawn once the entire evolution of spacetime is known. Much as a watershed can be fully identified only when we know where the water on each side will eventually flow, a horizon is recognized by the final destinations of light rays. For a white hole, this global character creates an exceptionally quiet ending. Matter inside may begin moving outward exactly as the idealized solution allows. Some of that emission escapes, spreads into space, and carries energy away. Meanwhile, gas or radiation from the environment approaches, increasing the gravitational mass around the region. The future horizon expands far enough to enclose what remains of the outgoing flow, preventing the white hole from releasing any substantial amount of additional matter. From far away, an observer might record a brief episode of emission, followed by a fading signal. This would not necessarily mean that all the matter inside had been expelled. Most of it might still remain behind the new boundary, where its light no longer has any path to the observer. The object was originally called a white hole because it could release matter, but once that ability is cut off, the old name no longer accurately describes the structure that remains. The transition into a black hole does not require the interior to reverse direction like a stream of water suddenly turning back. In general relativity, what matters is not whether the matter wants to continue outward, but which future paths remain open to it. Once the light cones tilt far enough, every future directed motion becomes confined within the new boundary. Matter may still move locally, but no trajectory can carry it into the distant universe. Light cones are the way physicists represent the directions signals can travel from each event. In nearly flat space, light can move outward in many directions, while slower moving matter remains within the limits set by those rays. Near a strong gravitational field, the cones tilt. Inside a black hole, the tilt becomes so extreme that every future direction leads deeper into the trapped region. In an ideal white hole, the light cones are arranged so that future paths open outward. When accreting matter changes the geometry, that arrangement can no longer be maintained. The new horizon marks the place where the light cones have tilted just far enough for the path to distant space to disappear. The region of spacetime that once acted as an exit becomes a place whose future is sealed. This is the more precise meaning of saying that a white hole is transformed into a black hole. No white sphere gradually turns black, and no object needs to flip over in space. The causal relationships around it have changed. Events that once could send signals outward can no longer do so. And in astronomy, that difference determines everything an observer can ever know. A region that cannot send light to us also cannot reveal the changes taking place inside. The remaining information comes from matter outside the horizon, from light that escaped before the exit was covered, and from the gravitational field of the mass that remains. Once the initial disturbances settle, the object may appear increasingly similar to an ordinary black hole when viewed from far away. This resemblance makes the death of a white hole harder to recognize than an ordinary destruction of matter. When a star explodes, its expanding layers of gas can be followed for years. When a planet collides with another object, heat, debris, and light preserve a record of the event. When a white hole loses its defining character, the most important part of the transformation occurs behind a boundary that prevents information from escaping. The observable signature, may be brief, weak, or easily confused with many other high-energy phenomena. The image of a new horizon covering the exit must also be treated with some caution. In different models, the distribution of matter, the rate of accretion, and the original geometry may alter how the process unfolds. Not every structure called a white hole in modern theories must follow exactly the same detailed history. The strongest conclusion applies to long-lived classical white holes. They are extremely sensitive to matter in their surroundings, and accretion can cause their emission phase to be cut off by a black hole structure. This sensitivity explains why the amount of matter that triggers the transition does not need to rival the mass of the white hole itself. A thin layer of gas does not directly fill the entire interior. Its importance lies in the time and place where its energy meets the outgoing flow. Near the horizon, these two streams moving in opposite directions can generate gravitational feedback far greater than intuition based on the weak environment at a distance might suggest. Research following Eardley's work clarified that, within the models considered, a white hole may cease producing significant emission on a timescale connected to its mass. This does not mean that every white hole in every theory possesses the same countdown clock. It shows that the classical version cannot easily remain active across astronomical lengths of time, while matter from its surroundings continues to accrete. A more massive white hole would have a different characteristic timescale from a smaller one. But the essential requirement remains unchanged. For the exit to stay open, the surrounding environment must remain sufficiently clean throughout the period of emission. Real space never possesses that kind of absolute purity. Background radiation, thin gas, and extremely small disturbances may arrive slowly. But the longer the white hole survives, the more opportunities they have to approach its horizon. Seen from this perspective, lifetime becomes a central part of the problem. A white hole does not need to resist the entire universe at once. It only needs to survive long enough for the right disturbance to appear. Once the exit has been enclosed by a future horizon, the passage of additional time does not help the matter inside find another route. The causal directions have already been rearranged, and the object continues to exist in a form better suited to its surrounding environment. There is an almost silent quality to this fate. Light that was once able to escape continues on its journey if it moved beyond the dangerous region early enough. Photons, arriving later, carry no sign that they have just lost their path outward. They simply follow the routes space-time allows. The new boundary makes no sound, does not slam shut in a single instant, and leaves no empty space where the white hole once existed. It merely divides the future in a different way. The final result is not complete disappearance, but a change in physical identity. The mass that once belonged to a region allowing matter only to emerge now lies behind the horizon of a black hole. The universe does not need to destroy the white hole in the ordinary sense. It only needs to retain whatever the white hole did not have time to release. At this point, the central question becomes clearer. An object that allows everything only to move outward can still be defeated by things approaching it, because external matter does not need to pass through an entrance. Its energy changes the geometry, and the new geometry causes the exit to stop leading outside. The absolute protection found in the idealized solution becomes a state that is difficult to preserve once the white hole must share space-time with the rest of the universe. Time is no longer a neutral background. Every passing moment brings more light, matter, and disturbance toward the horizon, while the white hole must preserve a structure that is already extremely sensitive. The longer it waits to release what lies inside, the more opportunities it gives the surrounding environment to build a new horizon around it. The exit may exist within the equations, but its lifetime depends on whether the universe leaves it undisturbed for long enough. A mountain can stand for millions of years without preserving every individual grain of stone. Small pieces are constantly cracking, sliding away, or being worn down by wind and water, while its larger form remains. A star does not survive by resisting every change, either. Matter is always moving inside it. Heat is continuously flowing outward, and its fuel is gradually being transformed, yet its overall balance can persist for periods far longer than all of human history. For most stable objects, time serves as a test, showing that small disturbances are not enough to erase their essential nature. A classical white hole faces almost the opposite situation. A long lifetime does not necessarily prove that it is more durable. It simply extends the period during which it must preserve a structure that is exceptionally difficult to protect. Every passing moment gives distant light another opportunity to reach it, allows thin gas to continue moving under gravity, and lets extremely weak disturbances travel through the spacetime surrounding its horizon. None of these influences needs to carry an unusually large amount of energy. The challenge is that the white hole must preserve the causal orientation of its exit within an environment that never becomes completely still. If a structure exists only for an extremely brief time, the chance of a significant flow of matter reaching it may be very small. A white hole that survives for thousands or millions of years, however, must face countless signals arriving from different distances and different moments in history. Photons moving toward it may have left their sources long before the white hole formed, while distant clouds of gas may slowly change their orbits and gradually move deeper into its gravitational field. The space around the object may still appear quiet, but that quiet is created by motions too sparse and too slow for ordinary senses to notice. Not because everything has truly stopped. A black hole adapts to this kind of environment in a fairly natural way. When gas falls inward, its mass increases and its horizon expands to enclose the newly added energy. After a merger, the surrounding spacetime may vibrate strongly, release gravitational waves, and gradually settle into a different configuration. A black hole does not need to preserve the same size or rate of rotation in order to remain a black hole. It can change with its environment while retaining its basic ability to trap signals that have crossed the horizon. A white hole does not have the same flexibility because its defining character depends on a boundary that allows matter to move only outward. When light or gas approaches from outside, its energy shifts the geometry around the horizon away from the ideal configuration. If that deviation grows strong enough, a new future horizon may form and surround the region preparing to release matter. The exit is not destroyed by a single violent collision. It gradually disappears as paths of light that once led toward distant space can no longer preserve that future. Time makes this process troubling, not because it carries a destructive force of its own, but because it extends the opportunity for small disturbances to appear and grow. A weak stream of radiation lasting only a few moments may not alter the geometry significantly. The same stream continuing over a very long period carries more total energy and creates more opportunities for signals to become blue-shifted and concentrated near the horizon. The longer a white hole waits before completing its emission, the more time the surrounding environment has to push its boundary away from its original state. This fragility can be pictured through a layer of snow resting on a mountainside after several windless days. Each new snowflake is far too light to produce any visible change, and the slope may preserve its stillness for many hours. Beneath the surface, however, the weight is slowly increasing. Crystals are gradually shifting, and small bonds are constantly being rearranged. Eventually, the final disturbance may be far smaller than the entire mass of snow above it. Yet the state has become so sensitive that even a slight deviation is enough to set a larger movement in motion. A white hole does not collapse like snow, but the similarity lies in the way time quietly makes the test more difficult. A sensitive state may endure many small disturbances without changing immediately, yet every encounter makes the assumption of a perfectly clean environment less realistic. What the white hole must protect is not a material surface, but an exceptionally delicate relationship among paths through space-time, where a small amount of energy arriving in the right region at the right moment may redirect the future of the entire system. The role of time becomes especially clear in models proposing that a black hole may transform into a white hole. Classical general relativity carries the collapse toward a singular region, where density rises until the familiar description is no longer sufficient. Some approaches to quantum gravity suggest that the contraction may be halted and then turn into an expanding phase, eventually allowing matter to emerge in the form of a white hole. Deep inside, this transition is sometimes described as taking place over a relatively short interval, while a distant observer may have to wait far longer because the strong gravitational field causes time to pass very differently between the two regions. At first, this long delay may seem helpful, allowing a black hole to survive for astronomical ages before releasing what has fallen into it. Yet while the inner process is waiting to be completed, the object continues to share space with the rest of the universe. Gas may fall toward it, background radiation continues to pass through. Matter from a companion star may form an accretion disk, and distant gravitational disturbances keep traveling across the horizon region. By the time the final white hole phase attempts to open an outward path, the external environment may have changed dramatically from the near vacuum state assumed when the process began. Studies of the stability of black hole to white hole transitions suggest that this long waiting period may become a serious weakness. Even a modest amount of matter arriving during that time may create a new horizon and trap the material attempting to escape. The white hole does not fail because its interior lacks enough energy to expand, but because the external geometry has had enough time to rearrange itself before the emission becomes visible from far away. There is no single number describing how long every white hole could survive. The timescale depends on its mass, its initial structure, its rate of emission, and the particular model being considered. A macroscopic white hole in classical general relativity cannot be evaluated in the same way as a remnant near the Planck scale, where quantum effects may completely alter how spacetime behaves. The more important conclusion lies in the general relationship. The longer the waiting time, the more demanding the requirement for isolation from the environment becomes. That isolation must not exist only at the moment the white hole appears. It must be maintained throughout the entire period before all the matter inside has escaped. A distant cloud of gas may need thousands of years to reach the central region, while light from an even more distant star may take longer still to complete its journey. If the white hole survives long enough, signals that seemed unrelated at the beginning may eventually become part of the environment surrounding its horizon. Every new history entering the problem creates another possibility for the structure to drift away from the ideal solution. There are countless ways for a photon, a grain of dust, or a stream of gas to approach at an unfavorable moment, while the number of histories in which the entire surrounding region remains perfectly undisturbed is extraordinarily small. Time does not need to increase the strength of each disturbance. Simply allowing more disturbances to appear one after another is enough to reduce the likelihood of long-term survival. Here, a white hole differs from a black hole not only in the direction matter travels, but also in the way each one moves through time. A black hole can continue to exist by absorbing whatever its surroundings bring, changing its mass and adjusting its horizon to a new configuration. A white hole must keep an exit open while external energy continually pushes the surrounding geometry away from its original form. One can grow because of what falls into it. The other can lose its defining nature because of things that never cross its boundary at all. These results do not close off every possible form a white hole might take. They mainly show that large, long-lived versions face severe difficulty in the presence of disturbances. A faster process might leave the environment too little time to produce strong feedback, much as a flash of lightning completes its entire event before the surrounding conditions can change significantly. In that case, a white hole would not need to preserve a stable structure for millions of years. It would only need to appear, release matter, and end within a period shorter than the time required for the instability to develop. This possibility changes how the concept itself may be understood. Perhaps a white hole, if it exists, would not resemble a durable celestial object resting in one place in space, but something closer to a brief transitional phase of spacetime. It would not compete with a star in longevity, nor would it need to demonstrate stability across immense spans of time. Its entire significance might lie in a single interval when matter finds a path outward before a new horizon closes around it. Even a brief moment can send light across enormous distances, deposit energy into the surrounding environment, and become a genuine physical event. What remains uncertain is whether the universe has any mechanism capable of producing such a rapid phase of emission, while also allowing it to avoid the instabilities that make long-lived white holes so difficult to sustain. The question of lifetime now becomes a question of speed. How quickly would a white hole need to complete its process before time itself had enough opportunity to turn against it? In astronomy, not every phenomenon needs to endure as long as a star or planet in order to leave a trace. A supernova reaches its greatest brightness for only a relatively short time, yet the matter it ejects may continue expanding for thousands of years. Two neutron stars merge within a brief instant, while the gravitational ripples produced by the event can travel across millions of light years before reaching instruments on Earth. Some things do not exist as lasting objects. Their entire significance lies in a transformation rapid enough to release energy and leave its mark on the history of the universe. White holes may belong to this class of phenomena. Instead of remaining in one place and continuously releasing matter for millions of years, a white hole might appear only as a brief phase in the evolution of a region of spacetime. The exit would open for a limited interval, matter from within would be released, and the white hole structure would end before the surrounding environment had enough time to alter the horizon. Such a possibility does not eliminate the problem of instability, but it changes the nature of the competition. The white hole would no longer need to resist the universe indefinitely. It would only need to complete its process faster than the disturbances could develop. The word fast does not correspond to a single number that applies in every case. 1 second may be extremely long for a microscopic process, but almost meaningless compared with the lifetime of a star, and time measured near a powerful gravitational field differs from time recorded by a distant clock. What matters is the comparison between two timescales: the interval required for the white hole phase to release its matter, and the interval required for energy from the environment to accumulate, reshape the geometry, and cover the exit. If the first process is completed sooner, the white hole may avoid the fate of longer-lived structures. Light and external matter would still be present, but their influence would not have enough time to grow decisive. The horizon would open, the stream of matter would pass through, and the transitional phase would end before the surrounding geometry had been completely rewritten. In this case, the white hole would resemble a gap that appears only briefly between two states, rather than a door that must be held open within a constantly changing environment. Some black hole to white hole models begin with the idea that gravitational collapse does not continue forever toward a point of infinite density. When matter is compressed into a regime where classical general relativity is no longer sufficient, quantum effects within spacetime may become important. These effects have been proposed as a mechanism that could slow the contraction, bring it to a halt, or turn it into expansion. The region that once functioned as the interior of a black hole might then enter a phase with the character of a white hole, allowing matter to move outward again. This remains a theoretical possibility because we do not yet possess a fully tested theory of quantum gravity capable of describing exactly what happens in the deepest regions of a black hole. Different models predict different transition times, geometries, and observable signals. Their shared idea is simply that collapse may not end at a place where every physical description breaks down, but may instead continue through a new state that does not appear in classical physics. When researchers examine the stability of such transitions, they find that time determines not only when the matter emerges, but whether the exit still exists when the matter reaches it. A process delayed for too long allows extremely weak streams of external energy to approach the horizon, become concentrated, and produce gravitational feedback. A new horizon may form before the white hole phase is complete, trapping the flow of matter that is trying to escape. The black hole would then remain a black hole, even if a rebound had already begun deep inside. A rapid transition avoids part of this difficulty by narrowing the period during which the environment can interfere. A distant layer of gas may not have enough time to approach, while faint incoming signals may not become sufficiently concentrated to create a new horizon. The matter inside would not have to wait through an astronomically long history before being released, making the requirement for an almost perfectly clean environment less severe. The difference can be pictured through a body of water slowly freezing over. If a small opening must remain clear for several days, ice will continue forming around its edges until the passage may eventually close. But if the water needs to flow through only briefly before the temperature falls far enough, the movement may be completed before the surface freezes. The environment has not disappeared, and the freezing process has not stopped. The process requiring protection simply ends before the threat can fully develop. A transient white hole would not become stable in the familiar sense. It would not endure a disturbance and return to its original state the way a star may recover after an oscillation. The white hole phase would exist only long enough to complete the release of matter, after which there would be no need to preserve the old structure. Its survival would be measured by whether the process reached completion, not by how many years the object continued to exist. This perspective helps resolve part of the tension between the equations and the surrounding environment. A long-lived classical white hole requires both a precisely arranged past and a region of space almost entirely free of disturbances, two conditions that are exceedingly difficult to find in nature. A short phase does not remove the requirement for a special initial structure, but it greatly reduces the time during which that structure must resist the rest of the universe. The fragile state does not need to become durable. It only needs to avoid breaking down before the sequence it has begun is complete. Yet the fact that a mathematical model survives disturbances does not prove that nature actually creates it. We would still need to know what triggers the transition, how energy is conserved, how the geometry connects the black hole region to the white hole region, and which quantum effects are strong enough to alter the collapse. Each question leads physics into a regime where direct observation is nearly impossible, because light from within a classical black hole cannot carry information back outside before the new phase begins. Even the idea of a bounce must be used carefully. It easily suggests a ball striking the ground and rebounding, but there is no solid surface inside a black hole for matter to collide with. If such a bounce occurs, it would be a change in the way radius, density, and the direction of time evolve within the geometry. Matter once drawn into a contracting region would enter a domain where future paths gradually open outward. The motion would not simply reverse within an unchanged space. Space and time around it would themselves have taken on a different structure. For a distant observer, the signal from a brief phase might not appear as a direct image of a white hole. Light could be bent, stretched, or altered through interactions with surrounding matter before escaping. If the release carried a large amount of energy within a short interval, it might resemble other explosive astronomical phenomena. If the energy emerged more gradually, or at wavelengths that are difficult to observe, the event could remain faint among the countless sources scattered across the sky. No observed burst has been confirmed as evidence of a white hole. Gamma-ray bursts, fast radio bursts, and other high-energy events all have known astronomical mechanisms or explanations still under active investigation, so they cannot be linked to white holes merely because they are brief and powerful. A convincing candidate would need to carry a distinctive signature of the transition, while also ruling out ordinary explanations through sufficiently clear data. This observational difficulty does not diminish the theoretical value of transient white holes. It forces the idea to change shape in response to what instability studies have revealed. If a stable white hole can hardly survive in the real universe, physics may instead search for a structure that does not need to survive for long. The question is no longer where a white hole may have remained for millions of years, but whether spacetime has ever opened an outward passage for a moment and then closed it before we had any chance to recognize what had happened. A brief event may still release a great amount of matter, just as a momentary merger can produce gravitational waves powerful enough to cross the universe. Duration alone does not determine the importance of a phenomenon. A phase that lasts only a short time where it occurs may still create a longer signal as the released matter interacts with its surroundings, much as a single knock can leave vibrations moving through a much larger structure. The appeal of this possibility lies in its modesty. The white hole is no longer presented as a long-lived, symmetrical counterpart existing alongside the black hole. It appears only during a brief interval in history, when the geometry changes from trapping matter to allowing it to emerge. That moment may be too brief for the classical instability to develop fully, yet still real enough to alter the energy and information that can reach the universe outside. Behind this temporary solution, however, lies another layer of difficulty. Even if ordinary gas and light do not have enough time to disrupt the process, the space around the horizon is never completely still at the quantum level. Fields remain present even in the vacuum state, and a rapidly changing geometry may act upon those smallest fluctuations themselves. A fleeting white hole might avoid prolonged accretion, but it may not escape the response of the quantum vacuum, as the outward passage appears and then disappears. Even if all ordinary gas, dust, and light surrounding a white hole could be removed, the space left behind would still not become absolutely empty in the way modern physics describes nature. The absence of drifting atoms does not mean that all activity has stopped, because beneath the world of individual particles lie quantum fields extending throughout space. They exist even in places where no instrument detects a photon, an electron, or any other ordinary particle of matter. The vacuum is therefore not complete absence, but the quietest state those fields can reach. This quiet is different from an emptied room. In a room, objects can be carried away until nothing remains but the air and the walls. With quantum fields, there is no empty foundation beneath them that can also be removed. Fields are part of the way nature exists, while familiar particles can be understood as excited states of those fields. Photons are associated with the electromagnetic field, electrons with the electron field, and even when no particles are detected, the fields retain fluctuations and correlations that cannot be eliminated completely. Saying that the vacuum fluctuates can sometimes create the image of tiny particles constantly appearing and disappearing like bubbles in water. That picture may be useful at a very basic level, but it does not fully capture the nature of the problem. The quantum vacuum is not simply a container filled with countless hidden particles appearing at random. It is the lowest energy state of the fields, in which certain quantities cannot all be fixed with absolute precision at the same time. That uncertainty leaves behind fluctuations and correlations capable of producing measurable effects when the field encounters boundaries, acceleration, or a changing geometry of spacetime. In flat, stable space, the concept of a particle is usually fairly clear. A detector can register an incoming photon, measure its energy, and distinguish that signal from the vacuum state. Near a strong gravitational field, the distinction becomes more subtle because the passage of time and the way field oscillations are divided into frequencies depend on both the observer's motion and the surrounding geometry. A state described as containing no particles by one observer may not be described in exactly the same way by another. The Unruh effect provides a famous example of this subtlety. Someone moving uniformly through a vacuum may detect no thermal bath of particles, while a detector undergoing constant acceleration through the same region of spacetime responds as though it were immersed in an environment with a temperature. There is no ordinary cloud of particles already present for one observer to see while the other misses it. The difference arises from the relationship between the detector's motion and the fluctuations of the field. Black holes bring this connection between vacuum, gravity, and quantum particles to a much larger scale. When quantum fields are studied on the geometry of a black hole that forms and then persists, a state regarded as vacuum in the past may correspond to a flow of particles in the future. This is the foundation of Hawking radiation, in which a distant observer may receive thermal radiation even though the classical description of a black hole speaks only of a region that traps light. The particles are not drawn from some hidden reservoir beside the horizon. They emerge from the way the quantum state of the field evolves through a spacetime with a particular structure. If black hole geometry can cause the vacuum to reveal itself as radiation, its time-reversed geometry raises a corresponding question. How would a quantum field respond to a horizon that allows matter only to emerge, especially if that horizon does not continue forever but ends at some point? Robert Wald and Sriram Ramaswamy pursued this question in the late 1970s. Rather than placing a few individual particles around a white hole and following their trajectories, they examined quantum fields across the entire spacetime background of the structure. This approach allowed them to test something deeper than classical instability. Even if the initial environment contained no obvious stream of accreting matter, would the vacuum state truly remain quiet as the white hole horizon approached its endpoint? In the model they studied, the answer offered little reassurance. As the white hole horizon ended, the initial quantum state could evolve into an extremely intense stream of particles traveling toward the distant future. In the idealized description, the energy associated with this flow increased without limit, much as classical radiation had previously been blue-shifted and concentrated near the horizon. The problem no longer came from a cloud of gas already present outside. It arose from the response of the quantum field itself to the white hole geometry. The infinite growth produced by the calculation should not be understood as a prediction that nature truly creates an infinite amount of energy. When such a result appears, it usually signals that the original assumptions cannot remain valid all the way to the endpoint. The calculation treated the geometry as a fixed background on which the quantum field evolved. But if the field's energy becomes extremely large, the geometry itself must respond. Spacetime cannot remain unchanged while an enormous flow of energy passes through it. Gravitational backreaction would alter the structure before the idealized infinite value could ever be reached. The physical meaning lies in the instability, not in the infinity itself. Equality. This interpretation resembles Eardley's result at a deeper level. In the classical instability, external gas or light approaches the horizon, becomes amplified there, and causes the exit to be covered. In the quantum version, even the state called vacuum may respond to the structure of the horizon and generate an energy source that is no longer small. After this result, the emptiness surrounding a white hole becomes even harder to protect. One might previously have hoped that placing the object far enough from stars, gas, and dust would make classical disturbances negligible. Quantum physics shows that reducing the density of matter almost to zero still does not remove every response from the environment. The fields do not leave that region of space, and even their lowest energy state depends on how spacetime is arranged. This dependence becomes especially strong when a horizon forms, changes, or ends. A completely unchanging geometry may allow the field's oscillations to be classified according to a stable rhythm. When the geometry changes, that classification changes with it. Oscillations that belong to the vacuum state in the past may no longer count as vacuum in the future, and the difference may appear as real particles detected far away. A gentle comparison can be made with a musical string resting quietly in a room. If its length and tension remain fixed, its natural modes of vibration do not change. But if the point holding the string moves rapidly, the old modes no longer match the new structure, and energy may be transferred into vibrations that were not present before. A quantum field is not a material string, and space-time geometry is not a hand pulling it, but the comparison helps show how a changing background can turn a previously quiet state into one containing particles. The endpoint of a white hole horizon is especially sensitive, because it is where the structure allowing matter only to emerge no longer continues in its previous form. Oscillations that have traveled along the horizon for an extended period become connected with signals reaching the distant future, and the relationship between them may produce extremely strong amplification. A small change in the initial state may not remove the effect, because it arises from the way the entire geometry connects the past with the future. Even so, the result obtained by Wald and Ramaswamy was not a declaration that quantum physics rules out every possible idea of a white hole. Their work used an idealized white hole background and specific assumptions about the field's initial state. Modern transition models may confine the white hole region to a brief interval, alter the geometry near the horizon, or include quantum back reaction from the beginning, rather than placing a field on a fixed spacetime. When those assumptions change, the precise form of the particle flux may change as well. This caution is especially important because quantum field theory in curved spacetime is still not a complete theory of quantum gravity. It keeps the geometry classical while quantizing the matter fields that live upon it. This method is extremely powerful when the curvature has not become too extreme, but near regions where spacetime itself must undergo quantum fluctuations, the boundary between background and matter is no longer clear. To understand how a black hole might truly become a white hole, both matter and geometry may need to be described in quantum terms. The 1980 result nevertheless leaves behind a warning that is difficult to ignore. If a white hole model remains stable only when quantum fields are assumed to be perfectly silent, then the model has not solved the problem, because the vacuum does not possess the absolute silence that the geometry requires. The fields respond to the structure of the horizon, react to its evolution, and may carry energy outward in a way that makes the original background impossible to sustain. The paradox of the white hole now deepens by another layer. Ordinary matter can disrupt it without ever entering the interior, while the quantum vacuum can create instability even when it contains no obvious stream of particles to begin with. The more completely one tries to isolate the structure from the surrounding universe, the closer one comes to a level of nature where the very idea of perfect isolation loses its meaning. Space may still appear empty and peaceful on every ordinary scale. A distant detector might record no particles for a very long time, while the temperature of the environment falls close to its lowest possible level. Beneath that stillness, quantum fields remain connected to the surrounding geometry, waiting for changes in the horizon to reveal their state in a different form. A classical white hole does not seem to be saved simply by removing gas and light. When the exit opens and then comes to an end, the emptiness around it may itself become a source of quantum feedback. Its fragility is no longer merely an accident caused by a passing cloud, but may be tied to a deeper structure of nature, where vacuum, particles, and spacetime are never completely separate from one another. Yet the same quantum physics that makes the problem more difficult may also open the only path by which a white hole could be born. Classical general relativity provides no natural way for collapsing matter to reverse its course, but a quantum theory of gravity may alter the deepest region before a singularity can form. What was once regarded as the endpoint of every trajectory might instead become a transitional domain, connecting the contraction of a black hole to an expanding phase with the character of a white hole. The quantum vacuum does not protect a white hole through silence, but quantum geometry may give it a different origin. To know whether that possibility can avoid the instabilities already encountered, or merely transform them into another form, we must look deeper into the region where general relativity can no longer tell the whole story, where matter is compressed so intensely that space-time itself may have to change the way it exists. A collapsing star does not stop simply because its matter has crossed the horizon. Inside that region, the distances between layers of matter continue to shrink, density rises, and every future directed path leads deeper toward the central domain. General relativity describes this process with remarkable accuracy across the scales we can test. But as the contraction approaches its most extreme limit, the theory itself begins to signal that it may no longer be able to tell the final part of the story. That signal is the singularity, where the quantities describing the curvature of spacetime grow without limit in the classical solution. A singularity should not necessarily be imagined, as an infinitely small object sitting at the center of a black hole. It is closer to a boundary of the model, where paths through spacetime come to an end and equations that once worked extraordinarily well no longer provide a complete physical evolution. General relativity carries matter to that point, but it cannot say what might happen once the curvature enters a regime where the quantum effects of spacetime itself can no longer be ignored. Quantum mechanics governs atoms, elementary particles, and processes occurring on the smallest scales. General relativity, meanwhile, describes gravity as the continuous geometry of space and time. Both theories have survived demanding experimental tests, yet they have not been fully combined into a framework that can be applied with confidence at the center of a black hole. The place where matter is compressed most severely is also where the two great descriptions of modern physics must speak at once, even though a common language between them is still being developed. Some models of quantum gravity propose that the singularity is not the true end. As the curvature approaches the Planck scale, the extremely small regime where the quantum structure of spacetime may become apparent, the contraction could be altered. Spacetime may no longer behave like a continuous surface that can be compressed indefinitely, but instead respond according to rules absent from the classical description. The collapse might then slow, reach a state of maximum compression, and turn into expansion. Physicists often call this possibility a quantum bounce. The name may suggest matter striking a surface and rebounding, but there is no solid floor inside a black hole for such a collision to occur. If the bounce exists, it belongs to the geometry itself. A contracting region of spacetime changes into one whose geometric layers are expanding. Matter does not reverse direction inside an unchanging container. The container, the distances within it, and the direction of the future all change together. Before the transition, matter occupies a trapped region, where even future-directed rays of light move towards smaller radii. Afterward, the geometry may take on the character of an anti-trapped region, where future-directed light rays move outward. The transition between these two structures forms the foundation of the idea that a black hole could become a white hole. A region that once accepted matter without releasing it would eventually enter a phase capable of returning what had been trapped. This description is not a direct result of classical general relativity. If Einstein's equations alone are applied under ordinary conditions, the collapse continues toward the singularity. To open a path into a white hole, there must be a quantum region where the classical geometry is modified. The size, duration, and precise nature of that region vary from one model to another, because physics does not yet possess a single experimentally confirmed theory of quantum gravity. One widely studied proposal suggests that the transformation could occur through quantum tunneling. In quantum mechanics, a system can sometimes pass from one state to another even when the classical path between them is forbidden. A particle trapped behind a potential barrier still has some probability of appearing on the other side, not because it climbed over the barrier along a familiar trajectory, but because its quantum state is more spread out than the simple picture of a moving point would suggest. For a black hole, what tunnels would not be a single particle, but the geometric structure of an entire region of spacetime. A geometry containing a black hole horizon could transition into one containing a white hole horizon through a domain where quantum effects become strong enough. This does not mean that the whole black hole vanishes and reappears somewhere else. For most of the process, the exterior region may remain close to the familiar geometry, while the decisive change is concentrated around the transitional domain. Haggard and Ravelli developed a model in which the transition from black hole to white hole occurs very quickly as measured by a clock near the bounce region, while a distant observer may have to wait far longer. The difference arises from the extreme gravitational time dilation surrounding the black hole. A finite interval inside does not necessarily correspond to the same passage of time far away, so the event may be brief for the collapsing matter, while extending across a substantial portion of cosmic history when viewed from outside. This unusual feature helps explain why an internal bounce, even if it has already occurred, may not immediately appear in the sky. Matter could pass through the quantum region in a relatively short amount of proper time, while its outward emergence remains greatly delayed for a distant observer. The black hole continues to appear stable, gathering matter and interacting with its environment, even though the deep interior has entered a stage that the classical description no longer captures fully. That long delay also brings back the instability problem encountered earlier. While the transition remains hidden, gas and radiation from outside can continue approaching the horizon. If too much energy accumulates, the white hole exit may be covered by a new horizon before the matter can escape. A convincing transition model must do more than remove the singularity. It must also explain how the white hole phase survives the real environment surrounding a black hole. Some versions adjust the transition time or allow most of the black hole phase to proceed normally before the transformation into a white hole occurs near the end of evaporation. In this picture, the black hole first loses mass gradually through Hawking radiation. Its horizon shrinks extremely slowly, while the interior may preserve a volume and history far greater than its small exterior size would suggest. Once the mass approaches the Planck scale, the transition into a white hole could occur within a much smaller structure, where instability arguments developed for macroscopic white holes may no longer apply in exactly the same way. More recent geometric constructions have attempted to describe this path more clearly without allowing a singularity to form. In these models, collapsing matter creates a trapped black hole region, passes through a domain modified by quantum effects, and then enters an anti-trapped region with white hole properties. Outside the small quantum domain, Einstein's equations may continue to work almost normally. The unknown physics is confined to the place where curvature becomes sufficiently strong, rather than requiring the entire spacetime around the object to become quantum mechanical. This approach has an obvious appeal. It preserves the success of general relativity wherever the theory has already been tested, while opening a passage through the region where the classical solution leads to a singularity. The black hole is not replaced by something completely unfamiliar as soon as it forms. It may continue to exist, rotate, gather matter, and emit radiation much as astronomical observations suggest, with the decisive difference appearing only at a very deep or very late stage. Even so, a geometry that can be written down is not necessarily the geometry nature chooses. Effective equations may describe a non-singular process, but a complete quantum theory is still needed to calculate the probability of the transition, the waiting time, and its stability. Research involving spin foams, loop quantum gravity, and semiclassical models approaches the question from several directions, but none of these proposals has yet been confirmed through observation. Quantum tunneling also does not guarantee that every black hole will become a white hole in the same way. The probability of such a transition may depend strongly on the black hole's mass, internal state, and accretion history. Stellar mass black holes, supermassive black holes at the centers of galaxies, and hypothetical black holes formed in the early universe may not share the same timescale. A mechanism that matters for an object near the Planck mass could be almost impossible for a black hole that remains extremely large. This caution preserves the boundary between a serious scientific possibility and a conclusion not yet supported by evidence. No astronomical signal has forced us to conclude that a black hole has bounced into a white hole. Images of the shadowed regions around black holes, gravitational waves from mergers, and the motion of stars near galactic centers all agree remarkably well with ordinary black hole descriptions. These observations do not reveal the deep region where the proposed bounce would occur, nor have they detected a distinct release phase capable of ruling out other explanations. The value of these models does not lie in having already solved the fate of black holes, but in allowing physics to ask the question more clearly. Is the singularity truly the end? Or does it simply signal that classical geometry has been pushed beyond its range of validity? If spacetime has a quantum structure, could contraction turn into expansion while preserving the continuity of matter's history? And if the matter eventually emerges, In what form might the information that once fell into the black hole be returned to the universe? These questions connect directly to the black hole information paradox. Quantum mechanics generally requires that information about an initial state not be completely erased, while a black hole that evaporates entirely in the simplest description seems to cause the information that fell into it to disappear. A white hole phase has been proposed as a path through which information preserved within the interior might eventually escape. The possibility is appealing, but the release must remain consistent with limits involving energy, entropy, and stability, leaving the problem far from resolved. Within this picture lies a subtle reversal. Matter that once crossed the horizon does not immediately return, nor does it destroy the black hole from within through a simple explosion. It enters a region where time and geometry are arranged in ways that differ from ordinary intuition, passes through a quantum domain that cannot yet be observed directly, and may emerge in the distant future as part of a white hole phase. If this process exists, a white hole would not need to be created separately by the universe, with the perfectly prepared past required by the classical solution. Its past would be the black hole that existed before it. The emerging matter would not appear from a singularity already embedded in the infinitely distant past, but would continue the history of matter that once collapsed inward. This is how quantum gravity might overcome the problem of origin that has followed the idea of white holes from the beginning. The cost of this explanation is that the resulting white hole may look very different from the perfectly symmetrical counterpart found in the Schwarzschild solution. It may be small, survive only for a limited time, and carry the imprint of the long evaporation process that preceded it. Rather than a vast celestial object continuously releasing matter, it would be closer to the final remnant of a gravitational history that unfolded over an immense span of time. Where physics once saw an absolute ending, quantum theory may open another passage. But that continuation has not yet taken on a definite form. A bounce within a black hole remains a possibility developed through increasingly detailed models, not an event that has been observed. It keeps the story of white holes suspended between two realms, serious enough for science to continue calculating, yet still too far from observation to be considered a known part of the universe. If a black hole can truly pass through a quantum region and become a white hole, the version most likely to survive may not be a large object retaining its original mass. After a prolonged period of evaporation, what remains could be so small as to be almost invisible to every telescope, while the space inside still carries the imprint of a history far greater than its outward appearance would suggest. After radiating Hawking radiation for an immense length of time, a black hole is expected to grow progressively lighter. The process is so slow that a black hole with roughly the mass of a star would need far longer than the present age of the universe to approach its final stage. Throughout most of that history, the horizon shrinks almost imperceptibly, the temperature gradually rises, and the energy that once contributed to the object's mass is continuously carried away as faint radiation. If the semi-classical description is simply extended all the way to the end, the black hole becomes smaller and smaller until the curvature around it approaches a regime where general relativity can no longer provide a reliable answer. Its size may then draw close to the Planck scale, a realm so small that familiar ideas of distance and geometry may need to be replaced by a quantum theory of gravity. The question is no longer merely how quickly the black hole evaporates, but what remains when spacetime itself can no longer be treated as a smooth background. Some models propose that this final stage does not lead to complete disappearance. The object may transition from a very small black hole into a remnant with white hole properties, carrying a mass close to the Planck mass. Despite its grand-sounding name, the Planck mass in everyday units is comparable to that of a very tiny speck of dust, while the associated radius lies at a scale almost unimaginably smaller than an atom. From the outside, such a remnant might resemble an elementary particle more than a celestial object. Its tiny exterior can easily suggest that the interior must have shrunk by the same amount, like a box compressed until almost no room remains inside. But black hole geometry does not follow that Euclidean intuition. The area of the horizon and the volume of the interior do not necessarily decrease together in the way a rubber ball contracts. Under some choices of space-time slicing, the interior of a black hole may continue to grow even as the area of its outer horizon gradually becomes smaller. An old black hole may therefore appear extremely small near the end of evaporation, while still inheriting an internal region stretched across an immense history. That interior space is not a room neatly contained within a tiny sphere in the ordinary sense. It is a consequence of curved geometry, where the meaning of inside extends along space-time slices, unlike the way volume is measured in daily life. A gentle comparison can be made with a bag that has a very narrow opening, but a body extending far below it. From the outside, only the small entrance is visible, while the space connected behind it is much larger. The image is not entirely accurate, because the bag still exists within a larger space, whereas the black hole's interior is itself part of space-time geometry. Even so, it helps separate two quantities that are often treated as though they were the same: the size observable from outside and the amount of space existing beyond the horizon. In the white hole remnant scenario, this large internal region does not immediately disappear when the external mass falls near the Planck scale. It is carried through the transition, leaving an object that appears tiny from outside but remains connected to a deep internal history. The interior may contain information about the matter that once fell into the black hole, while its connection to the surrounding universe has been reduced to an extremely small area. This is why remnants are sometimes discussed in relation to the black hole information problem. If a black hole disappears completely after evaporation, physics must explain where the information about everything that once fell into it has gone. A remnant with a large interior provides a place where that information might continue to exist and then be released very slowly through a white hole phase. Instead of everything returning in one brief explosion, the information could leave through a narrow channel over a much longer period. This possibility does not automatically solve the information paradox. A model must still explain how the information is encoded, how quickly it escapes, and whether its release preserves the principles of quantum mechanics. A large interior merely creates room for a solution. It does not provide the full solution by itself. Still, it weakens the intuition that an object appearing tiny from outside must be incapable of preserving a complex history. The stability problem that makes large white holes difficult to sustain also looks different at smaller scales. A macroscopic white hole may have its horizon altered by external matter, causing the exit to be covered almost immediately. For a remnant near the Planck scale, the amount of energy required to change its state, the quantum nature of horizon area, and the possible superposition of black hole and white hole states may create a very different problem. Some research in loop quantum gravity suggests that a minimum horizon area could prevent the object from shrinking without limit, while allowing it to persist in a nearly stable state. The word stable must remain within the limits of the model. It does not mean that the remnant has been proven immortal, nor does it guarantee that every disturbance would be harmless. The arguments depend on how spacetime is quantized and on assumptions that cannot yet be tested directly. What they suggest is that conclusions about the instability of large white holes may not transfer unchanged to a tiny object near the Planck scale. Part of this difference comes from scale itself. A remnant does not need to maintain an exit wide enough to release enormous layers of matter over a long period. It may release energy and information very slowly through a region with only a tiny connection to the space outside. The ordinary environment may also interact only weakly with an object whose cross-sectional area is extremely small, making direct collisions far less likely than they would be for a macroscopic celestial body. If such remnants survive for long enough, another question arises: could they make up part of the dark matter? Dark matter is recognized mainly through its gravitational effects and does not emit light in the way ordinary stars and gas do. A population of small, durable remnants that interact only weakly with light appears to possess some properties that fit this description. Some models have explored the possibility that tiny black holes formed in the early universe, evaporated, and left behind white hole remnants that have survived until today. Appealing as this idea may be, it remains far from a discovery. No evidence has confirmed that dark matter is made of white hole remnants, and their formation rate, lifetime, and distribution depend on many assumptions about the early universe. Current observations of dark matter could also be explained by many other unidentified particles or structures. White hole remnants remain only one candidate within a much broader field of research, not the answer that has been selected by the evidence. The greatest difficulty is that an extremely small object producing almost no light would be very hard to identify through a distinctive signal. The gravity of an individual remnant would also be weak because of its low mass, making it difficult to detect through the motion of stars in the way larger black holes are found. To recognize such a population, scientists might need to search for cumulative effects on the formation of cosmic structure, rare interaction events, or a characteristic form of radiation released when a remnant finally decays. Even if an unusual signal were recorded, proving that it came from a white hole would remain a challenge. The universe contains many phenomena capable of producing brief flashes of energy, faint particle streams, or subtle gravitational deviations. Convincing evidence would need to agree with the remnant model, while also resisting ordinary explanations involving known astronomical sources or elementary particles. Until then, these objects remain part of the map already outlined by mathematics, but not yet illuminated by telescopes. A white hole remnant presents an image very different from the enormous object that often appears in popular descriptions. It does not violently eject matter in the middle of a galaxy, nor does it shine as an easily recognizable source of energy. It may be tiny, cold, and almost silent, carrying only a modest mass on the outside, while remaining connected to an internal region that preserves traces of the black hole that existed before it. If this scenario is correct, the universe may contain the final remnants of ancient collapses without revealing them through light. Each remnant would resemble a piece of history folded into the geometry, with an opening too small for the entire story to escape all at once. What once fell inward would not necessarily be lost. It would simply remain preserved within a structure whose outer size does not reveal the full depth of its interior. The elegance of the idea cannot replace evidence, but it expands the question of white holes in a less intuitive direction. Perhaps large versions are destroyed by the universe almost as soon as they appear, while the versions most likely to survive are too small to be seen directly. In that case, white holes would not have failed completely. They would have survived only by giving up the form of a large celestial object and becoming remnants almost indistinguishable from the surrounding darkness. The rest of the story belongs to observation. If white holes cannot survive for long on large scales and are nearly invisible on small ones, what does their absence from the sky truly mean? It may indicate that nature has never created them, but it may also reflect a more troubling possibility for astronomy: that these structures appear too quickly, too faintly, or too quietly for our current instruments to recognize. The sky has provided us with many lines of evidence for objects with the properties of black holes, even though an event horizon itself cannot be seen like the surface of a planet. Stars orbiting rapidly around a dark mass at the center of the Milky Way, hot gas emitting X-rays as it falls deep into a gravitational field, ripples in spacetime reaching Earth after mergers, and dark regions surrounded by strongly bent light all fit the picture of an extremely compact object capable of trapping light. These observations come from different methods, yet they converge on a class of objects for which black holes provide the most natural explanation. White holes have no comparable chain of evidence. No source of light, explosive event, or gravitational signal has been confirmed by the scientific community as matter emerging from a horizon that opens only outward. This absence does not automatically prove that white holes are completely impossible, but it creates an enormous gap between two structures that appear symmetrical in the equations. One has entered the realm of observational astronomy. The other still exists mainly within mathematical solutions and untested models of quantum gravity. The first difficulty lies in their outward appearance. From far enough away, the gravitational field around a spherical object depends mainly on its mass and does not directly reveal every detail of the spacetime hidden deep inside. A black hole and a white hole with the same mass could produce nearly identical orbits in the matter surrounding them. Passing light would still be bent, nearby clocks would still experience gravitational time dilation, and distant matter would still feel an attraction toward the central region. The name white hole sometimes leads people to expect a brilliantly luminous object that continuously pushes everything away, but its gravity does not become anti-gravity. If no matter is escaping at the moment of observation, measurements of the external gravitational field alone may not be enough to determine whether the horizon beneath it has the character of a black hole or a white hole. The crucial difference lies in the direction that light and matter can travel through the region very close to the boundary, where future paths open either inward or outward. Astronomy often observes compact objects through the environments surrounding them. A bright disk of hot gas can reveal that matter is losing energy and moving toward the center, but most of the signal comes from a region that still lies outside the horizon. An image of a black hole's shadow is also created by light emitted from the surrounding plasma and bent by gravity, rather than by a direct photograph of the horizon's surface. If a white hole differs from a black hole only within a very thin region near the boundary, distant measurements would need extraordinary precision to detect the distinction. A long-lived white hole might be easier to discover if it continuously released matter, but this is also the kind of structure most vulnerable to instability. Gas and radiation approaching from outside could cause its exit to become covered, ending the emission phase before the object survived long enough to be recognized as a distinct celestial body. A macroscopic white hole in the classical description might transform so quickly that the sky would never contain a stable population of them, comparable to stars or black holes. In that case, we should not search for a fixed point of light that remains visible for many years, but for a transitional event. Matter might escape over a brief interval, interact with its surroundings, and leave behind an expanding flow of radiation. By the time a telescope turned toward that location, the white hole structure might already have ended, leaving only light, particles, and hot gas slowly cooling. A brief event introduces a second difficulty. The universe already has many ways to create powerful bursts. Massive stars can explode. Neutron stars with extremely strong magnetic fields can release energy suddenly. Merging compact objects can produce gamma-ray flashes, and sources of plasma can generate very short radio signals. Each phenomenon carries its own history, environment, and energy spectrum, but when the available data are limited, many events may look similar during the first stage of observation. A mysterious flash does not become evidence of a white hole simply because it is powerful or brief. A convincing identification would require the model to predict a sufficiently distinctive set of signatures: the timing of the energy release, the evolution of the radiation spectrum, whether gravitational waves accompany it, the composition of the ejected matter, and the response of the surrounding environment. Those signatures would also need to be difficult to explain through known astronomical mechanisms. Current black hole to white hole transition models do not yet agree on these details. Some scenarios predict that matter is released during a rapid phase. Others place the white hole at the very end of a prolonged evaporation process, while remnant models predict objects that are tiny and weakly interacting. When the theory itself does not provide a single signal pattern, designing an observational search becomes more difficult. A telescope may record an unusual event, yet there may be no reliable standard for connecting it uniquely to a white hole structure. Remnants near the Planck scale create a different kind of silence. If their mass is only comparable to that of a tiny speck of dust, and their external size lies near the quantum scale, individual objects would be almost impossible to image directly. They would have no large surface from which to shine. The gravitational field of each remnant would be extremely weak at ordinary distances, and their interaction cross-section with matter might be so small that significant encounters would be exceedingly rare. A large population of such remnants could leave a collective influence on the evolution of the universe, but a shared effect would reveal little about the nature of each individual object. Dark matter is also detected mainly through gravity, which is why white hole remnants have sometimes been proposed as candidates. But the fact that a model can provide dark matter does not mean current observations have selected it. Many other particles and objects could produce similar gravitational effects. Even if remnants occasionally decayed or released information, the signal might be extremely faint, exceedingly rare, or located in an energy range that has not been monitored widely enough. Astronomy does not observe the entire sky, at every wavelength, at every moment. Observatories have limits in sensitivity, operating time, and the regions of space toward which they are pointed. A short event may occur between two surveys, while a faint signal may disappear beneath the background or be removed from the data as noise. Cosmic distances make every trace even fainter. Light from a distant transition may be stretched to longer wavelengths as space expands, while ejected matter must travel through the intergalactic environment before reaching the region near Earth. The original signal may be altered significantly, making features that were clear at the source difficult to recognize after billions of years of travel. None of these obstacles should be used to shield the white hole hypothesis from every observational result. A scientific hypothesis must still make predictions that can be tested, at least in principle. If every signal could be explained as a white hole, yet no signal could ever rule the idea out, the concept would lose its ability to distinguish a physical model from an untestable possibility. Modern research is attempting to narrow this gap by constructing more specific transition geometries, tracing the paths of light, calculating radiation spectra, and searching for possible accompanying gravitational wave patterns. This work remains at an early stage because even a small change in the transition time, mass, or structure near the horizon can alter the predicted signal. Until a sufficiently clear observational signature emerges, the most accurate statement remains that white holes have not been found. The silence of the current data is consistent with several possibilities. Nature may never create white holes, large versions may become unstable too quickly. Brief phases may blend in with other cosmic bursts, while tiny remnants may be almost invisible. Each possibility leads to the same observable sky we see today, yet carries a very different physical meaning. This absence is precisely what keeps the question of white holes open without turning it into a mystical mystery. Science does not always need to choose immediately between existence and non-existence when the evidence remains incomplete. It can keep several models side by side, test each prediction, and gradually eliminate the versions that fail to match observation. Long-lived classical white holes have faced strong objections because of their instability, while brief phases and quantum remnants still await clearer tests. Perhaps we have never seen a white hole because the universe simply does not build them. Or perhaps they appear only in moments that are too brief, at scales that are too small, or behind signals that resemble other phenomena too closely. The difference between those answers will not come from discovering a single bright point labeled as a white hole, but from many measurements converging. Light near horizons, gravitational waves, the energy spectra of transient events, and the way matter behaves around regions of extremely strong gravity. Until then, white holes remain at the boundary between a possibility opened by the equations and an object that has not yet entered the observational map. Their absence does not diminish the value of the mathematics, but it reminds us that the universe is under no obligation to realize every structure we are able to write down. Some possibilities are ruled out by the conditions required for their formation. Some may survive only for an instant. Others may exist too quietly to be recognized by the instruments we have today. After all these layers of instability, time, and quantum physics, the original question has taken on a clearer form. A white hole may not survive for long because it must preserve a very unusual exit within a universe that is always bringing energy toward it. If that exit is covered, the object becomes a black hole. If the process ends quickly enough, its traces may drift away before they can be identified. And if a remnant survives at an extremely small scale, its presence may blend into the darkest part of the universe. Things we have not seen are not always entirely absent, but science can move forward only when that silence begins to leave a signal clear enough to measure. The white hole is still waiting for such a sign or for future observations to close the possibility that the equations once opened so quietly. White holes began as a possibility hidden within the equations of gravity, where space-time can be arranged in a far wider variety of ways than anything humanity has ever observed. Within that structure, a region that allows matter only to emerge remains perfectly valid mathematically, just as a black hole is a region that allows matter to enter without returning. The two directions appear symmetrical on paper, but once placed within the real universe, that symmetry quickly encounters limits the idealized equations never needed to face. Black holes can be born from the deaths of massive stars, the mergers of compact objects, or other gravitational processes that have left clear traces in the data. They do not require every particle of matter to arrive at exactly the right place and time, because many different histories can still lead to the same region enclosed by a horizon. A classical white hole requires a far more tightly arranged past, in which matter, light, and geometry must work together to create an exit that allows nothing from outside to enter. Even if that rare state could form, the space surrounding it would never be truly empty. Faint photons would still pass through, thin gas would continue to move, and ancient radiation would still spread a very low background of energy across the universe. Each component on its own might be too weak to significantly affect a star or planet, but a white hole is not held together by its mass alone. Its existence depends on the way paths of light and directions into the future are arranged near the horizon. A photon does not need to cross into the interior to help alter that structure. As light and matter approach the boundary, their energy contributes to the curvature of space-time, while blue shift can make disturbances that were initially extremely weak increasingly important. The horizon is not a wall standing apart from its surroundings, so the exit is not protected like a doorway hidden behind a solid shell. It is part of a geometry that responds to every form of energy present around it. The fate of a white hole would not necessarily take the form of a violent destruction. A new future horizon could form and surround the region that once allowed matter to escape. The mass would not disappear, and the space-time inside would remain, but the paths leading toward the distant universe would have changed. The object would lose its white hole character not because it had been erased from existence, but because the future of the light rays inside would no longer open outward as it once did. The longer this continues, the more demanding the test becomes. A structure that exists only for a brief moment may complete its process before the environment has time to create strong feedback. A white hole that survives across astronomical ages, however, must keep its exit open against countless streams of radiation and matter arriving one after another. A long lifetime, usually associated with stability, may instead become a weakness when every passing moment creates another opportunity for a small disturbance to redirect the geometry. Quantum physics offers no absolute silence, either. Even if ordinary gas and light were removed, quantum fields would remain in their vacuum state. They respond to horizons, curvature, and changes in space-time, meaning that an ideal white hole structure may still encounter instability within a region that appears completely devoid of matter. The deepest emptiness in nature still contains fluctuations and correlations that cannot simply be taken away. Yet it is within this same layer of physics that a white hole may acquire a different origin. Some models propose that a black hole does not end at a singularity, but passes through a quantum region where contraction turns into expansion. The phase that follows may have white hole properties, allowing matter that once fell inward to continue its history in a new direction. This has not been observed, but it changes the question from how a white hole might be created to how a black hole might transform once general relativity is no longer enough. The version most likely to survive within these models may not be a large and luminous celestial body. It might be only a rapid phase that ends before instability can fully develop, or a remnant near the Planck scale, whose exterior is extraordinarily small while its interior remains far larger. If such structures exist, they may be too brief to be recognized as stable objects, or too quiet for present-day telescopes to distinguish them from the darkest parts of the universe. The absence of evidence does not allow us to say that every form of white hole is impossible. It only reminds us that many steps lie between a mathematical solution and an observable object. A mechanism of formation, resistance to disturbances, a sufficient lifetime, and a signal distinctive enough to separate it from other phenomena. Black holes have passed these tests through many independent kinds of observation, while white holes still stand at the boundary between models and reality. Perhaps the universe never creates them, or perhaps white holes appear only in moments too brief to be seen directly, or at scales too small to leave a clear trace. Science does not need to choose too quickly between these possibilities. Each model must continue making predictions, waiting for data, and accepting rejection when observation fails to agree. The value of white holes does not depend entirely on whether they are ever found. The concept shows that equations can open the way to elegant structures, while nature continues to ask more difficult questions. How could such a structure form? How would it withstand its environment? And could it survive long enough to become part of the history of the universe? A white hole may be permitted to appear, but that permission has never been a guarantee. Among passing light, moving matter, and quantum fields that are never completely still, its exit must preserve an exceedingly rare order. Even a slight change in the geometry may close the future that once opened outward, leaving that region of spacetime to continue existing in the form of a black hole. Perhaps this is the deepest lesson a white hole leaves behind. The laws of physics do not merely describe what is present. They also outline a vast landscape of possibilities. Some possibilities are built by the universe into stars, planets, and galaxies. Some appear only for an instant. Others may be entirely valid, yet too fragile to endure. Within the distance between equations and reality, the white hole remains like a question that has not yet closed. It reminds us that the universe does not need to reject a possibility by forbidding it from existing. Sometimes, it is enough for light to continue passing, matter to continue moving, and time to continue flowing for even the most elegant structure to disappear before it can ever be seen.